Yeah, that's okay. Yeah, okay.
Does that work too?
Yeah,
Yeah.
I think, but you need to speak like not so loud.
Not too low, okay.
Because it's very, very loud.
I think when I stand up, it means they only have a minute.
Okay.
When I stand up and start to work, threatening to watch. That's
Sure,
I
it's mostly to Karin,
also
because
the
I'll do the first half.
slide for your presentation, because they need to change
Yeah.
something in my
I do the
settings
fun
of the
part.
screen. So when you do
Yeah.
the presentation, just take my laptop again.
So I'm going to use your laptop?
Yeah, because we check everything. Cool, cool.
Let's begin. Okay, so welcome to the quantum session. And we have a bunch of talks. And the first talk is from a bunch of authors from King's College London. And the first part of the talk will be given by Avner Ben-Susan.
Hi everyone, thanks for being here. It's actually great to have a quantum session in such a high quality conference. So today we'll present you AcceleRQ. That is our attempt to optimize quantum eigensolver with machine learning. And don't worry, I'll give you all the information you need about eigensolver to follow the talk. So, first of all, why do we need to optimize quantum software? So in a general use case, we used to have software engineers that built software, hopefully with some good practice about software. And it's for a specific audience, but here when we're talking about quantum software, it needs a lot of expertise on quantum physics actually to follow some basic quantum physics properties. So it's usually quantum experts that build those software, and they are aimed for quantum experts at the beginning, but it's now we have also a use case for medicine or financial use cases. So it's because of this very multidisciplinary aspect of quantum software that we gathered a multidisciplinary team in King's Quantum to try and see if our gather of knowledge can actually help optimizing those software. And we picked a very specific problem that is quantum eigensolver. And the only thing that you need to know about quantum eigensolvers for this talk is that it is search iterative process, and the aim is to find a specific property of a quantum system. Usually it's the minimal energy of a molecule, for example. And it's very hard to do. So you have to make an educated guess and go over it several times until you reach the desired output. And the most prominent quantum eigensolver that is out there right now is called a variational quantum eigensolver, and it's one of the examples that we go through the paper. If you want more details, we have very accessible definition of all this notion in the paper. But the principle is that you have noisy quantum hardware in the middle of a classical optimization loop, and you have to tweak some parameters and go over the quantum computation several times to actually find the results you want. But the problem is that those parameters need a lot of expertise actually to understand how they affect the computation. And so if we want to optimize it and to plug it into a machine learning loop, we want to abstract out those problems. So the first thing that we did for for this work is to basically take these algorithms and this instance of algorithm and put them into a box and go over all the parameters that can happen in this, that we have to tweak in this optimization. So that's the one example of such a parameter. And I guess you don't understand what it means, but maybe this guy does. And so when you talked with experts and you asked them if they ever switch to something different than the default parameter, for many of these parameters. Most of the time they say no. But when you work with them, you can actually define some boundaries and some structure of these notions. So that's what we did. And we basically created first layer of abstraction. And I'll let Karine explain you what we managed to do with this layer of abstraction.
Yeah. So we're going to treat everything from now on that we give to the simulator as a code. And to understand, first of all, how this code is working, because it's very complex, we don't have a lot of understanding. What we did at first, very classically, no computer, quantum computer involved, we start doing some data preparation. So instead of trying to do some very specific analysis or static analysis of the code, what we did, we took very small system and start sampling them with the implementation, with the code that we have. We sample them many times and create a set of data from very small samples, so we took some small system, we create some data array samples from systems. I think I will just look at the screen. And then we classically, because this is a very small system, we can just compute it mathematically based on the specific code that we have, because it implements something very specific. We compute the result, like the property we want to learn or to know from this system, and then we train some regressor, and then that's the part when the classical stuff ends. And then using this small train model that was trained on small system, we move to bigger system and we move it to the quantum computing. And then with this, we select different better relations. So these constants are not always just constant like 5, but they sometimes represent some relations. So if I put 5 here, then somewhere else maybe I need to put 200. And if I put 4, maybe then this 200 is no longer valid. I need to put a different number. So they have a bit more complex relationships there. And then we run we use this we deploy this model and find a better value for a specific large quantum system with this specific implementation with the code I have in my hand. So the code gets some quantum system and does something on it. Yeah. So and the code is just like Python code with a bit of libraries. And then we find the better numbers, and then we plug this number back into this implementation with the system we care about, and then we run it on a quantum computer, and hopefully we get better results. The problem is that this part is too greedy. So what usually machine learning does when it learns some function, it becomes very greedy. It will try to take maximum resources. It try to do a lot of things that doesn't make a lot of sense. And to understand it, you have to a little bit dive into the parameters there. So, for instance, this is some of the numbers and the meaning and the relationship that might involve that we took from when we analyze each of the code. So, for one of the implementations, we took 2 implementations. One called adapt QSCI, and the other one called QCells. They're both algorithm that solve the VQE problem. And we took 2 different implementations written by different people. And I just look at one of them because we don't have enough time, I think, to dive to all of it. So some of it's like num pickup, for instance, is how many, what is the level of abstraction? So how many elements inside my quantum system I'm actually pulling and giving to my code, to my implementation. Cutoff is the same. It's like if some elements are too small, when I can start ignoring them. So it's also part of the abstraction of the quantum problem, and so on. So all of these are very somehow control how much information I am taking out of my quantum problem and giving to the implementation to work on. Two very interesting things is the number of sampling shots. So we cannot sample as much as we can, and we cannot we cannot sample a million times, and we cannot run infinite amount of stuff in the computer. But what usually do when it's too greedy, they're trying to raise all these numbers. So they want to get maximum precision, a lot of very longer time so you can get better assurance of your number. So this is a pro, yeah? So this being too greedy, in that case, will give you very, very high accuracy, and you have a lot of freedom of what of the settings and the assumption on the quantum problem that you allow your algorithm, your code to know. Of course, the cons is that it's going to run very, very long time, and the gain might not be at some point we get to a plateau. But in reality, unfortunately, the hardware will terminate much earlier because we have quantum noise, and you have, so once you go to the hardware, you have a very limited time when you can, very, very limited time you can do the cycles and you can do the sampling. You cannot sample forever. You cannot run this software forever. That's because of how, in general, you can never run forever, but in quantum is much more aggressive. So we cannot run, so a good thing that we don't have extreme runtime because the hardware will stop much earlier, but we also lose the maximum accuracy. And to be honest, what happened in the end is we just we waste all our time at the beginning of the problem and not at the end of the optimization problem, and then we get very low accuracy. So what we did, we defined a set of relationships. So I know that I can have 200 iterations, but then each iteration I only have, 200 shots. But then if I will move it to 20 iterations, then I can have much more iteration during, much more shots during the iterations. And there are actually much more relationships, but and you probably need to go to the paper to understand this. I think just the number of shots and the iteration are the easiest to explain. So what we did to solve this greediness, we write a sequence of tests that either just look at what I told you, the number of iterations versus the number of shots during each iteration, and see that we are not sampling, we don't have too many shots in total, but there's other properties. So one of the things is self-selection, is when you can reuse some operator again, and there is the final, when we decide things related to the stopping condition. And we wrote tests. Some of the tests requires running some sample of the code of our implementation, of the VQE implementation, to see if the numbers make sense. Some of them you just can compute it statically. And what we did when we run the test, so the default is the default parameter. With the optimization, let's say it can have, let's say 0 and 1, and then if I do the test, then the test actually said, no, 1 is never possible, it doesn't make any sense, and then we remove this value to avoid this greediness that leads us to suboptimal solutions. G is about the stopping condition, so with the test you see that it can select much more broad number of values, and with the test you can see that the bottom values, the lower values are just chopped away because they're no longer making sense with this specific implementation. So these are some of the tests we wrote. So you can imagine that some of them will be, so the static one is here, which usually you can just check with this one. This is the number of iteration versus number of shots per iteration. And some of them are require running some code and observing the result, like a small part of, not the whole algorithm, a small part of it, and observing the results. So we run this, and there's half of the paper I think is evaluation, but just a little bit of the results that we got. If you look, the black line is, we can look at one of the algorithms. So the one with the black line is the default parameters, and let's say with the pink and the green one is, the pink is with the test, and with the green is with the, the pink is with the optimization only, and the green is the optimization with the tests. And you can see that, I don't know and you want, obviously, the value to be, so you want to look for the minimum value, yeah? So you can see that the green sometimes, and sometimes the pink are actually the one who's taking. The other implementation sometimes might have a better result, but if you just look at the adapt one, then you can see that the black here is up, and the green is sometimes below, and sometimes the one with just optimization wins, and We have similar results here. Here is a bit more noisy. This is the size of the system of 20, 28, and 24 and 28. Yeah, and that's all. I think the conclusion you can read, and when I prefer to leave it for questions now. Thank you.
Questions, anyone? We have a microphone. How long does this process take? The going through and picking the right hyperparameter for the biggest case of 28 qubits?
I think that this is not very, it is quite quick, like you can do it in an hour or two.
An hour or two?
But the evaluation to get these numbers, this takes months.
That takes a while.
That took 3 months for each system.
Running on a simulator or on a
And a simulator, yeah.
Okay, 3 months.
Yeah.
Very good. All right, thank you.
Thank you.
Very good. And the next talk is by Anita Bugley. And we're almost there. Please.
This talk is about quantum network protocols and how to quantify their behavior. Quantum networks are networks connecting quantum-capable devices. Now, all the talks in this session are interested in what's happening inside individual quantum devices. And we want to connect these devices together and make them communicate with each other. Each device in the network has a few of so-called communication qubits, designated to establish connections with other devices in the network. By being connected, we mean that distributed devices can share entanglement. Quantum networks bring benefits. For example, scaling of quantum computation, that it's also part of IBM Quantum Roadmap. Another benefit is that they enable secure communication with killer apps such as teleportation and entanglement-based quantum key distribution. Quantum networks are indeed becoming a reality. With test beds emerging across the world and entering practice, computer science is here to drive further advances in this area, and in this spirit we are here. Bell pair is the fundamental entanglement resource in quantum networks. Bell pair is just a pair of entangled qubits. This is a Bell pair model here at Art Science Museum in Singapore. We denote a Bell pair by a tilde connecting the nodes that contain the entangled qubits. Now, but one limitation of Bell pairs is that they carry no control information. Thus, quantum networks need to be built on top of classical ones. Classical networks consist of end nodes that are connected through switches via classical channels. On top of this, quantum networks have separate quantum channels, quantum-capable end nodes, and repeaters to overcome large distances. Some of these nodes can also act as quantum sources where Bell pairs are created locally. Now let's have a look how protocols run on such architectures. For simplicity, I'll present network's topology as a graph. In a classical network, a packet, which is the information carrier, is forwarded through switches from source to destination, hop by hop, 1 and 2. Below, we record the path that the packet has traveled. In quantum networks, however, qubits cannot be forwarded over large distances due to their decoherence and the no-cloning theorem. Now, let's describe our running protocol example that generates an end-to-end Bell pair between nodes A and B. The protocol runs in 3 rounds. In round 1, we create 2 Bell pairs locally at C. Below, I will write the execution traces that record the multiset of Bell pairs in each round. In round 2, we transmit 1 qubit of each pair to the neighbors, A and B. And in round 3, we perform so-called entanglement swapping. This action is Bell's measurement at C that exchanges the 2 Bell pairs into one over larger distance. This way, we generated Bell pair AB. Now, given that quantum networks work like this, we need to make sure that they behave as intended. With our previous work, we were able to address questions like, does a protocol establish Bell pairs between the specified nodes? Are 2 protocols equivalent? Or can protocols run in parallel? And as a solution, we provided a foundation to answer these types of questions, which we by designing the Bellcat language that we presented at PLDI last year. With the work I'm presenting today, we want to reason about quantitative properties of such protocols. And we want to answer questions, what are the probabilities at which our protocol produces AB? What is the expected number of protocol iterations? Or can we improve the rate at which Bell pairs are generated? And again, as a solution, we provide formalism to answer such questions by designing a language for quantifying quantum network protocols. The name PBCat stands for probabilistic Bellcat, that alludes to Bell pairs and Kleene algebra with tests cat. PBCat's key feature is that it captures probabilistic behavior for expressing failures and combines it with non-deterministic behavior that arises from concurrency. In what follows, I will introduce the language components through our running example. So in round 1, we create 2 CCs locally. In round 2, we concurrently transmit them to A and B. And in round 3, we swap them. The indices indicate the success probabilities of each action. And above, we will write the execution traces and assume that at the start we have no Bell pairs. So in round 1, we create 2 CCs locally with probability 0.81. But we may only succeed in creating 1 or none. If 2 CCs were created in round 1, in round 2, we transmitted them to AC and BC. But again, we might have only succeeded in transmitting 1 or none. The case where only 1 CC was created in round 1 becomes more interesting. Let's say that there is a scheduler that non-deterministically transmits CC to either AC or to BC. And the remaining case where no CCs were available after first one round, there is nothing to transmit. And finally, in round 3, the swap action can only attempt if it has both AC and BC available and succeeds with probability 0.6. And in all the remaining cases, if the swap doesn't get the required Bell pairs, so nothing happens. At the end, we combine, collect these traces into protocol output. How? The probability of each output multiset is obtained by compounding the probabilities along the paths that lead to it. So for example, we output the, is the cursor? Okay. We output the empty multiset with probability 0.29 by compounding, by summing up the paths here, along the black parts and the brown one. Thus, the probability distributions mu and mu prime come from non-deterministic choice. Finally, we present the output as a convex set of probability distributions. Why? Intuitively, each distribution in these convex sets corresponds to a different strategy of the scheduler. For example, if the scheduler prioritizes transmitting to AC, then we get this distribution. Or if the scheduler randomly transmits CC to AC or BC, then the output distribution is here in the middle. As you've just seen, we write PBCat protocols as expressions that consist of basic actions such as transmit and swap, guards that test for available bell pairs, together with constants for skip and abort, and we combine them with conditionals, sequential composition for transitioning through rounds, and while loops. We also have parallel composition and ordered composition that is a variant of parallel composition, where E always has priority over F when grabbing bell pairs. PBCat semantics is built in 2 steps. First, the abstract semantics interprets the PBCat expression as a guarded strings of sets of actions. And then the execution semantics produces the output, which is convex set of distributions like we saw in the example. We also implemented a tool that enables writing PBCat expressions in an embedded DSL inside Haskell. Here is a snippet. So F first creates CC locally, and then it conditionally transmits it. And below, F is in parallel combined with some other protocol E. So from an expression, the tool builds an automaton that captures the abstract semantics, and then it computes the execution traces, and it outputs the convex set of distributions. To summarize, we designed PBCat language for expressing real-world quantum network protocols. We prove soundness of its axioms with the semantics that enables protocol verification and optimization, and we built a prototype tool for quantitative analysis that we evaluated on 16 protocols that all took under 10 minutes to verify and used at most 8 gigabytes of memory. And with this, I thank you for your attention.
Thank you.
I have 2 questions. One is, when you have a probability of failure when transmitting, is that completely, I guess, classical, or is it like, I think of that as there's like some fidelity of the state I actually transmitted, or is it completely like?
So yes, it's classical in the sense that you treat the actions or operations as the black box, and actually the early generation schemes or protocols are going to be implemented so that you will get a heralding signal, which is a classical signal that will acknowledge the success or failure of your action. So you will know what you succeeded with.
I see. Cool. And my second question is, I don't know that much about quantum networks.
Yeah.
So are bell pairs like the only, I guess, primitive that we need in them? Or does this generalize to other types of entanglement?
So bell pairs are the resources of quantum networks, and you use them to run applications on top of them, right? Like teleportation, and each of these applications, to transmit the information with teleportation, for example, you will burn the bell pair. The same with, or you will use it to transmit. And yeah, so that's the work. Of course, there are many multipartite entanglements which are less stable. So the benefit of this is that they are maximal entangled bell pairs. So they are the strongly correlated as you can possibly find. So they are and easy to produce.
Oh, cool. Thank you.
could the next speaker come up and set up? But I have one more question for you. What's the largest example that you tried your new technique on?
So the examples are small, of course, because you have XP complete. Like
Yeah,
we
just move your computer.
we just generate all the traces.
Yeah.
But the complexity actually doesn't come from the size of the topology, but from these nested for loops.
Aha.
Okay, so that's why. So the examples that we have are like on 5 nodes and chains.
Okay, and that's already quite a challenge.
Yes.
Okay.
Yes.
Very good. Thank you again.
Is it working? It just worked before. Oh, no. Oh. Okay. Thank you so much.
Very good. The next talk is by Michael Metz, please.
Hello, I'm Mikhail, and I'm presenting this paper on compositional quantum control flow with efficient compilation in Unity, which was done in collaboration with Fane, Leah, and Robert. So the most prominent model of quantum computation that we typically see is this circuit model, and most ways of thinking about how to program quantum computers rely on this idea that we have some classical computer that maybe constructs a quantum circuit, sends it to a quantum computer, which then runs it, measures the qubits in the end, and sends the result back, right? And we can continue doing this and to represent some sort of quantum algorithm. However, this does not really feel like high-level programming, right? When we write classical programs, we typically don't represent them in terms of just logical gates, which is the equivalent of quantum gates. So the question we were trying to answer is, can we write quantum programs in a way that is high level, on a higher level of abstraction than the circuit model? And this is what the Unity language attempts to do. So the main goal of Unity is to try to take certain existing programming constructs from classical computing and try to generalize them in a natural way to quantum ones. So for example, we have notions of control flow, pattern matching, error handling, and some complex data structures that we want to have quantum versions of. So this was originally proposed in 2023 as kind of theoretical construction, and in this work we propose some extensions to the control flow features in Unity to improve its expressivity, and we implement the first compiler that converts Unity into low-level quantum circuits in OpenQASM. And we design various optimizations for this compilation process. So first, I'd like to start with this example of a famous quantum algorithm called Grover's algorithm. So the problem is we're given a function that takes in n bits and it outputs 1 bit, and we want to find an input to this function such that f outputs 1. So the basic idea of how Grover's algorithm works, right, is that we start in an equal superposition of all the inputs, and we try to repeatedly apply certain reflections of the quantum state using our function to rotate the quantum state around until it eventually gets closer to the correct value, right? It turns out this gives a quadratic speed up. So, okay, but how do we actually implement this on a quantum computer as a circuit, right? So first of all, our function f could be any function on n bits, and it might not be reversible. In most cases, it's not, right? But when we build quantum circuits, they are unitary and they have to be reversible. So first thing we have to do is we have to somehow encode our function into a quantum circuit. So the typical way of doing it is something like this, where we add in an extra ancillary qubit, and the circuit has to basically flip it depending on what the output of f is. So once we have that, then using a typical framework like Qiskit, where we are specifying how to construct the circuit, it will look something like this. So somehow this composes these circuits that will represent these reflections of the quantum state. But this doesn't really feel like something that's high level, and it's not entirely obvious from first glance that this corresponds to that picture of rotating the states and like how we think of the algorithm. So also, like, this idea that we have this function f, we have to first convert it into this quantum oracle that we then put into the circuit. But ideally, what we really want is we want to just write f as a function normally without worrying how it integrates with everything else, and then just be able to simply plug it in, right? So we want to use it as a subroutine without needing to worry about how to adapt it to this algorithm. And then another thing, what hypothetically we might want to even implement f with a quantum algorithm. Maybe it's some really complicated computation that we need to run a quantum computer on to find what it is, right? And another thing is, like, we have, this is running on functions from n bits to 1 bit, but what if we have maybe some complicated data structure that we really don't want to bother trying to figure out how to encode it into bits, right? So this is all the things that we want to happen in a high-level language, and this is what happens in Qnity. So here, this is our new syntax for the Qnity language, and this is what a Grover iteration looks like in Qnity. So first of all, you can see that it works for an arbitrary data type in Qnity, provided that we give it how to generate the equal superposition of a data type. And we can take in basically any function that accepts this data type and outputs a bit. And so then here it's very clear what this does. We have this control condition on the output of f, and we have this pattern matching. In this case, very simple. If it's 1, we apply a phase. And then after that, we just reflect it about the equal superposition. So the key thing that makes this work is this control construct. So in Qnity, the idea is that we allow to have these arbitrary quantum subroutines that we can condition on. However, for this to actually work and be physically realizable, the Qnity type system does have to impose a lot of restrictions on all the other parts of it. So this is the typing rule for control in Qnity, and kind of the main biggest constraints here are that, first of all, the patterns themselves that you're matching against have to be classical, and we have this erasure condition on the branches on the right-hand side of this block. And so this is needed because if you don't have these constraints, the semantics of this as a quantum operation might not be something physically meaningful. You might have something like increases the norm of a quantum state, which we don't want. But we might want to try to avoid these constraints, potentially trading off some of the capabilities of control, thus so that we have more flexibility on the kinds of quantum control flow we can do. And so this is what we did in the work, and we augmented Qnity with 2 additional control flow features. Here are called match and p-match. And so the idea is that they offer different trade-offs with the capabilities of control. So for example, match is designed to work just kind of as a match statement in classical languages. So it has very minimal restrictions on how you define the control flow structure. But unlike control, it itself does not have pure or reversible semantics. And then the other one is p-match, which is a form of kind of symmetric pattern matching between orthogonal sets of expressions. And here, unlike in control, we can have an arbitrary basis for all the patterns in the branches. But again, you don't have the subroutine capability. So here's just an example of how you might use match. So just to implement the AND gate, which is really simple and like the way you would do that just in classical programming. But the cool thing about this is you can easily just plug it into a quantum algorithm. So for instance, you can just use this and take it and put it as the F for Grover's algorithm. And it will work because the compiler will automatically figure out the purification and make this into that quantum circuit. And then here's an example of where you might use p-match. So we have this data type, which is maybe type that has 3 different values, and we want to prepare an equal superposition of this. So this is how you would do that with this p-match construct. But then if you were to use only control originally, you have to do this kind of ugly construction because of this erasure restriction. So essentially we'd have to do on computation manually, which we really want to try to avoid because kind of the goal in Qnity is to automate the process of on computation. Okay, so another thing you've been seeing through all these examples is the syntax this is written is really kind of a meta-programming layer above the core Qnity language. So in the actual language, we don't really have a notion of recursion or higher order functions because these things are notoriously difficult to extend in a meaningful way to quantum computation. There's some work that does that, but it doesn't really fit into the framework that we're doing with Qnity. So, but we do have these on the layer kind of above Qnity that gets preprocessed and converted into main language. So you can easily do things like, write the actual Grover that combines several iterations, starting with the equal superposition. Okay, so this is the process we have for compiling Qnity. We start with this high-level program. After preprocessing, we just have the Qnity core language. And I guess the interesting thing is that then we have all the typing rules in our language. So here's an example of just how the pair is typed into the product type of T0 and T1. And then that is converted into this intermediate representation. And the idea is that these are kind of these high-level circuits where instead of the wires representing individual qubits, they correspond to Qnity's data types or context. And so here, for example, you can have some quantum variables that are present in both E0 and E1, and that corresponds to just sharing them along the classical basis and plugging it into the corresponding circuits. However, if and that's then compiled down to low level circuits. But if you just naively do this implementation, if you just try to run something very simple, like this is an example of how you might do a CNOT gate, it compiles to something ridiculous initially, right? So we have to kind of try to figure out how to optimize this compilation process. So we'll look at this procedure and all the different stages of it. And on each stage, we tried changing something in the process to optimize it. So the first thing you can do is, of course, because like in the conversion to low-level circuits, you can just do some sort of standard post-processing techniques just for optimizing the circuits themselves. But this by itself is not really enough, and we have to do something on the previous stages. So here, for example, when converting from the intermediate representation, some things we did is figure out how to recycle qubits when it's possible, and also how to better construct circuits for the direct sum, which are essential for performing the pattern matching in the control flow constructs and representing different data types. And on a higher level, we also have ways to more efficiently construct the intermediate representation circuits themselves, using different ways to represent how to compile these orthogonal expressions in the pattern matching blocks, for example, and to efficiently transform it with the different types. So this is just an example of we ran this on various different benchmarks, and as you can see, there's a very significant improvement in the optimized compiler compared to our initial implementation. In many cases, it gets pretty close to the manual low-level circuit implementation, but in some cases, for more complicated algorithms, there's still a lot of room for improvement. To conclude, we have constructed the first Qnity compiler. We expanded the language itself with more enhanced control flow constructs, and we figured out several techniques to optimize the compilation. So in future work, something we could also do is try to compile to a different target and potentially include hybrid classical quantum programs in our final language. So thank you. This is a paper and the code. And thank you. Are there any questions?
Thank you. Questions, please.
Mm-hmm.
On one of the previous slides regarding optimizations, you mentioned that you do qubit recycling.
Yeah.
Qnity also supports errors. Have you investigated how qubit recycling affects errors, and what happens if you recycle a qubit when you're in an error state?
Yeah, so the idea is that we represent errors by having certain qubits for signaling them, right? So there are certain flag qubits that if they're in a one state, that represents that an error occurred. And so we can only recycle, so we can measure a qubit. If it's not inside a subroutine, that is an error, and after that we can recycle it. Or also if the type checker determines statically that a certain program is error-free, then we can just immediately know that this error qubit can just be immediately recycled.
Thank you.
Mm-hmm.
Thank you. We have to stop here. Sorry. Thanks again. Okay, let's see if you can get that going. Pretty good. Okay, now we get to the hard part. Next speaker is Abtin Molabi, please.
Hi, everybody. So today I'll be talking about our work on solving the unique connectivity constraints that arise in trying to compile circuits to error-corrected devices.
Oh.
Say something.
Hello? Okay. So yeah, like I mentioned, I'll be talking about our work on solving the unique connectivity constraints that arise in trying to compile circuits to error-corrected quantum devices. So as many of you here probably know, there's been a lot of interest in actually building quantum computers in the past couple of years from several major industry players. And the motivation behind this is some exciting applications that people see of quantum computers in the future, like Shor's algorithm for factoring large numbers, or the simulation of molecules for chemistry. But there's a roadblock on this way towards these interesting applications, which is that these large-scale applications require orders of magnitude more operations than we can directly apply to our quantum computers. Luckily, we have a solution for this problem, which is quantum error correction. So the basic idea of quantum error correction is that we use redundancy in order to drive our error rates arbitrarily low. So we encode one logical qubit using several physical qubits. One of the most popular approaches to quantum error correction is the surface code, and I've drawn a little cartoon of a surface code qubit here. This entire square patch represents one logical qubit, and each of the small circles represent a physical qubit. So the really exciting thing in the past couple of years is that we've seen physical implementations of the surface code. So we just a few years ago, we saw the first smallest scale examples of a distance 3 surface code. And then just last year, we saw a really exciting experiment out of Google where they were able to demonstrate this scaling property that I was discussing, where they created a small logical qubit and then a larger one, and noticed that the error rate did actually go down. So now that we have this hardware on the horizon, it's time to start asking the question of how we compile circuits for surface code devices, which is the focus of our work. So I showed you one of these logical qubits, and we can think of a surface code quantum device as like a plane of these logical qubits arranged in 2D. So we can represent this as a grid graph, where each of the vertices now is a logical qubit, and the edges represent pairs of logical qubits that are adjacent, but not the diagonal. So we end up with a grid graph. So given this representation of a device, let's think about how we could compile a circuit down to it. So first, we need to decide which of these logical qubits will represent the qubits that appear in our computation. So this is one example of such an assignment. And then we need to plan the execution of our 2-qubit gates. So it turns out that the way you implement a 2-qubit gate in the surface code involves finding a path between the 2 qubits that the 2-qubit gate acts on. So this is an example of a path for this particular gate. However, we cannot use 2 vertices in our graph at the same time for 2 different gates. So now we have this second gate that is logically parallel to our initial one, but it's physically blocked, so we can't execute it in the same time step. Instead, it must wait for the execution of the other gate and then execute in the next time step. On the other hand, if we had picked a slightly different arrangement of our qubits, we would be able to find a single-step execution. So our goal is to figure out how to compile our circuits while using the least number of time steps. So we call this the surface code mapping and routing problem. There are 2 inputs. On one hand, you have a circuit, which we're particularly focused on 2-qubit gates, and also the T gate, which is a single qubit gate, but it turns out that in order to implement it, you also need to do this sort of routing procedure. And then we also have some architecture that we'd like to execute the circuit on with certain distinguished vertices, which again are the routing endpoints for those T gates. And our goal is to find one of these schedules for executing the gates, and we want to minimize the number of time steps. And additionally, a small detail is that there's some constraints on the last edges of these paths. On one end, they need to be vertical, on the other end, they need to be horizontal. Okay. So our approach to this problem splits it up into 2 phases. It's an NP-complete problem, so our initial relaxation is to think about it as a mapping problem and then a routing problem. At the mapping phase, our insight is to take a dependency-aware view, so we're trying to predict which operations actually have the potential to conflict with one another. And then at the routing phase, our insight is that we want to search for the best order in which to route gates, which can perform significantly better than some fixed heuristic for gate routing order. And at both of these phases, we have a sort of unstructured discrete search that we implement via simulated annealing. So I'll start by talking about the mapping phase, which is how we're going to assign qubits in our circuit to locations on our grid graph. So one thing that you might do to solve this kind of mapping problem that we've seen in prior work is to construct something called an interaction graph. So this is a graph that corresponds to our circuit, where we introduce an edge for every pair of qubits that are involved in a 2-qubit gate. And this can give us some sense of what sorts of things should be mapped close together to avoid conflicts. But the problem occurs with certain circuits like this that have a high density of connectivity. So if we look at this circuit, we end up with a complete graph, which really gives us no information for mapping and routing. Basically, any map that we evaluate is going to be equivalent because of the symmetries in this graph. So we don't really learn anything from constructing the interaction graph. And so I think of this as analogous to like a flow-insensitive program analysis, because we're not tracking any information about when these interactions occur. On the other hand, in our work, we do have the simple extension that we call the layered interaction graph. So in this case, the first thing we do is we divide a circuit into layers of parallel operations, and then we augment the interaction graph with this information, basically. So we have a sequence of graphs now instead of just one graph. So now we have a flow-sensitive analysis. And the interesting thing we learn when we construct the layered interaction graph in this case is there's really only one pair of operations that we need to worry about. All of the other ones, there's no way to execute them in the same time step anyways because of the dependency structure of the circuit. So we really should just focus on a mapping that allows us to route these two gates in parallel. And so the way our dependency-aware mapping algorithm works is that it tries to minimize the number of conflicts. And we define a conflict as a pair of edges that we have labeled as occurring in the same layer and have overlapping bounding boxes with respect to a mapping. So let's look at an example. Here is one potential mapping of some qubits onto an architecture, and we draw the bounding boxes for each of these operations, which turned out to actually exactly coincide, so we have one conflict. On the other hand, if we choose this different mapping, the bounding boxes are now disjoint, so we have no conflicts. And it turns out that with this second mapping, we can route these gates in parallel, but with the first one, we can't. So our conflicts were able to capture that difference between these two mappings. So now I'm going to move on to talking about routing. So now that we have fixed a qubit mapping, how do we find a route for each of our gates? Well, one basic thing you would want to try is this greedy strategy, where we have some set of parallel gates, and in order to route them, we just iterate over them, find the shortest path that we can route each gate along, and then remove those vertices from our graph and continue. But there's something really interesting about this algorithm, that the order in which we iterate over the gates is going to matter. Because it's a greedy algorithm and we're changing the graph as we go, the order of iteration matters. And so the big question here is, how do we choose which order to iterate over the gates in? So just choosing some reasonable best gate first is going to give you a suboptimal result. So let's look at an example. So here we have one C0 gate and two T gates. And one reasonable heuristic that actually has some results from theory about its approximation ratio is to route the shortest gate first. So in this case, this is the shortest gate, but is the C0, but now we've blocked the two T gates from executing. On the other hand, there exists an order in which we can route the two T gates at the same time. So we should prefer this order if we can find it. And so that's why we perform a search over the possible orders. So we can do better than any fixed order by just searching over orders before committing to one. And an additional detail here is that we weigh our reward for routing a particular gate by the criticality of that gate. And that helps us avoid a long tail of operations at the end of our execution because we've been waiting on some critical gate. So now I'm going to transition into talking about our experimental results. We collected this pretty comprehensive benchmark suite of over 200 circuits, a lot of common algorithms and subroutines. So the closest related work to ours was something called AutoBraid that appeared in past work. AutoBraid did not try to route T gates, so here we're just focusing on the two qubit gates. And we're comparing against AutoBraid on two different architectures. The one on the left we call the square sparse architecture, which maybe you can see why. And then the one on the right is what we call the compact architecture. So here we're more resource constrained. This kind of represents a more near-term setting where we don't have 1 million qubits. And so we see on the square sparse architecture, the most common thing to happen is that AutoBraid and our approach called DASCOT find the same number of time steps. And this is because basically you can get very close to the optimal because you have a lot of routing space. But on the other hand, as we reduce the resources, there are a lot more cases, which is about 60% of them, where we find a solution that's strictly better than the one that AutoBraid finds. And our approach is especially well suited to the QFT, quantum Fourier transform circuits. And if you know a little bit about the structure of QFT, that might not be surprising based on the example I used to motivate the mapping algorithm that we use. So here we see the gap growing in the cost ratio, which is basically like the number of steps in your solution divided by the depth, which is the optimal possible solution that's growing as the number of qubits in our QFT increases. And a final experimental result is that we developed this SAT-based optimal baseline. So this solution does not scale at all. It only works for very small circuits where we encode basically the existence of a solution with k time steps into a SAT instance. And then if we find one, we turned it into a solution, and if not, we increment k. So in this way, we find an optimal solution. And what we find is that for almost all of our benchmarks, again, the ones where the SAT-based solution actually terminated, we're able to find solutions that are very close to optimal. They're just these 5 cases at the top where we're far away. So I'll conclude here. Check out the paper for some of the things I didn't have time to talk about, like the details of our SAT encoding, and also this work has been sort of integrated into our compiler WISC, which also does some other things from other papers. So go check that out as well. Thank you.
Thank you. Questions?
Hi, that was a great talk, thank you. So my question is a surprise. So I'm surprised that simulated annealing did so well. Okay. So what do you think is the reason, right? Because it's it's not supposed to be getting the optimal solution every time. So do you feel like that's something that will continue to be the case as you scale up, or is it like, what's your take on that? I'm just curious.
Yeah, that's an interesting question. I think that this is also saying something kind of about our the instances that we were able to find optimal solutions for. That they're very small, so you have a high probability of something like simulated annealing finding a good result. I don't necessarily expect it to continue to be this close as you scale up. If we had some way of knowing the optimal, but I don't have anything better that can actually solve those large instances. So.
Thank you.
Mm-hmm.
All right, thank you again. Okay, next speaker, Anirudh Piduri, please.
Hi, today I'll be talking about our work on quantum correctness by construction. This is joint work with Ina and Michael. I think this is something that we can all agree on, that the larger programs get, they often contain mistakes and bugs that we need to catch. And for over the last 6 or so decades, there have been many approaches to verifying these programs. Some based on logic, like Hoare logic and incorrectness logic, and model checking, analysis, testing, and so on. But interestingly, quantum algorithms present new challenges. The first, maybe more immediate one, is that we don't have enough hardware, so you can't do things like just run and test your program. And even if you could, you can't use standard debugging techniques like inspect the program state as you run, because measurements collapse the state and they disrupt the computation. So it's all the more important to be able to have formal methods to verify quantum programs. So we build our approach on a standard logic called Hoare logic to verifying programs. To recap, Hoare logic is you state program correctness as a Hoare triple, which is a precondition, a program, and a postcondition. And this Hoare triple is said to be valid if for every input that satisfies the precondition and you run the program, it has to, the output state has to satisfy the postcondition. And there are 2 methodologies of using Hoare logic to verify programs. The standard one, which was where it started by Tony Hoare, is called post hoc verification, where you take a program, you use the logic, you phrase the correctness constraints as these triples, and you build up a proof for the program. So this is a bottom-up approach where you take the entire program and you try to prove that it's correct. And there is another approach which we can use to also verify programs, which is called correct by construction or refinement programming, where you instead start with the specification of what you want your program to do, and you incrementally refine the program, build it step by step, while ensuring that each step that you do maintains the validity of the program. And this is like the opposite. This is a top-down approach where you can discover details on the fly, and this is somehow more closer to how one would actually discover an algorithm or build something, as opposed to being given a program to verify. So first, this standard logic has been extended to quantum logic, like for quantum Hoare logic, where we model our the pre and post conditions as quantum predicates, which are POVM elements, and the degree to which an element holds is given by the probability that if you measure the state with this P of M element, like the outcome, the probability that you get this outcome. And this is similar to how it's modeled in probabilistic logic. We also assume standard denotational semantics on quantum programs that map mixed states to mixed states, and these are in general arbitrary, like completely positive trace non-increasing maps that correspond to physically realizable quantum operations. And the correctness of a quantum Hoare triple, stated the same way, says intuitively says that the probability that the precondition holds on the input state is at most the probability that the post condition holds on the output state. And intuitively, this just says that things that were correct continue to remain correct, and I mean, you could have accidentally also made other things correct as you run the program. So we build our framework on a very standard programming language called the quantum while language, which is a basic statement-based instruction language with support for conditionals and unbounded loops based on classical measurement outcomes. That is, you measure some quantum register with a binary outcome, and depending on the classical measurement value, you decide whether to continue the loop or enter the branch. So we extend this with a hole which has a pre and post condition tag to it, and this is in principle the same way it is done for refinement programming with typed holes, where you tag a blank program with a type, and here we tag it with a pre and post condition. And what we want to do is, at the end, when you construct a program starting from a hole, you want the corresponding Hoare triple that you get to be valid. So how do we do this? We give a set of refinement rules that one can use to incrementally fill in the program. A refinement rule is of the form, you start with the hole and you can go into some other program S, possibly containing more blanks, when a certain set of conditions for it are satisfied. And the advantage of thinking this way is that once you perform a refinement and you know that it's correct, you can then forget the conditions that you've already checked and just focus on each independent, like each hole that you have in the remaining program independently without worrying about the structure of the program. I'll give a few examples of basic refinement rules that you can use. So each refinement rule comes accompanied with some particular condition that you would have to check. Either you check it immediately or you existentially quantify and then look at it later. So a simple example is if you initialize a quantum variable Q to, let's say, the 0 state, then you have to check this corresponding matrix constraint. Similarly, if you apply unitary, you'll have a constraint that says P implies U dagger QU. We can also just refine to a sequence of 2 steps with an arbitrary intermediate condition of choice. And maybe the more interesting rules are first bounded loops. If you want to repeat, if you want to refine to a repeat statement that repeats n times, the body has to satisfy a family of constraints where Rj is the property that's true after the jth iteration, and then after running the loop body once, like you basically make one step. And this, we can extend the same to unbounded loops that says that, yeah, if you refine an arbitrary hole P blank Q by running a measurement B on a quantum register Q, both picked by the person like building the program, then you'll get a similar family of holes that where you have these series of predicates R0, R1, so on, with some particular limit R. And intuitively, this hole captures that the assertion Rn captures the fact that the state will run in the loop for at most n iterations. So the condition for the hole says that if you start with a state that would quit after n+1 iterations and run the body, and then after performing the measurement, either you get the outcome 0 and then it satisfies the post condition because you've exited the loop, or you get the measurement outcome 1, that's B1, and then it satisfies Rn, that is, it would only continue for n more iterations. So we show that our refinement system that we give is both sound and complete, that is, any constructed program is correct, and we can also construct any valid program that can be proven in the corresponding Hoare logic using using some sequence of refinement rules. we show a few examples in the paper to capture standard patterns that people can find useful to build larger programs. One common example is the repeat until success pattern, which is used, for example, in magic state distillation and so on. So this is one possible refinement rule that you can use to get the repeat until success pattern, which is the I here is the identity operator, which says any state. So the whole you have says, starting with any state, I want an output that satisfies Q. Then you can refine it to a loop that says you keep measuring the variable Q with the orthogonal complement of this predicate Q. And you have two requirements that you need to satisfy. The first one says that if you start in the orthogonal complement of Q, then with probability epsilon, you will end up with a state that satisfies Q that says each loop iteration works with probability epsilon. And this is something that you can pick while refining the program. And the second one effectively states that the program terminates. That is, you start with something in the orthogonal complement of Q, and you'll end up with a program that terminates, which basically says that the loop body terminates, preventing the loop from diverging. We also show a few more constructions for Grovers and QFT in the paper, which I will have to omit for lack of time. Yeah, so we basically built a starting step towards bringing ideas from refinement programming to verifying quantum programs. But there are naturally more things that we like to look at. One is use more expressive languages like we've seen in the talks before, and also capture more high-level patterns. Repeat until success is a nice pattern, but it would be nice to have amplitude amplification as a first-order pattern in the language, in the refinement calculus, and also use other calculi to maybe say build efficient programs by construction using an expected runtime calculus, for example. And it will also be nice to look at ways to use concrete assertion language to efficiently represent these predicates, and then mechanize checking these conditions using like libraries that are capable of doing it in Coq and so on. So to summarize, we give like a framework to use refinement programming to build correct quantum programs, like programs that are correct by construction, and you can use this to refine to large programs and focus on one part at a time. And as you, through the refinement process, it helps you focus on each subpart of the program, and you can decide on the choices that you have to make along the way, and you can easily extend it by adding new like refinement rules based on the ones that we already have. Yeah, thank you for listening.
Very good. So I just want to comment on your future work there. I think if you could do oblivious amplitude amplification, that would be very cool. So the flavor of what you're doing has some synthesis to it, right? That you like to discover things as you go. How do you think of your work versus other papers we know that do synthesis without thinking about Hall logic?
Without thinking about what?
Hall logic.
I see. So I guess you can use this as one way to do synthesis. Like if there is like a synthesis-based tool that uses Hall logic as its specification language, then it would be one way to automate maybe some easier parts of the program. Like larger parts of the algorithm are usually hard to synthesize just automatically.
Right.
But maybe smaller steps can be synthesized, yes.
Do you run into some kind of scalability problems like other approaches to synthesis do sometimes?
No, so in this we've only given the theory, so we've not implemented it. So that's future. Okay, so.
Hi, I'm Cesar from MPI SP. So did you have to define I suppose you had to define a Hall triple for each of the operations of your language, right?
For the refinement rules, yes, that's correct. Yeah.
Okay, and did you look into to build like a weakest precondition calculus for this, or?
Yeah, so actually, if you look at the rules for the basic statements, these are effectively the weakest precondition rules. The right side term here is the weakest precondition of Q with respect to this program, and P is so you need to have P implies that, and of course for larger programs it's hard to get the weakest precondition.
Okay.
For more complex programs, but yeah, for basic statements, it is effectively the weakest precondition. Yeah.
Okay, thank you.
Other questions? Very good, thank you. Okay, and the next talk is coming up. The first speaker will again be Arnab and Susan, as you've seen before. And this is my chance to say that the second speaker, both last time and this time, is Karine Evan Mendoza.
No, this
That is confusing. Okay, so the third speaker, so now there's a third speaker, but I think it's roughly from the same group at King's College. Very good. Okay, so sorry, that was me being confused. The third speaker is Vasileios Klimis. But we start with you, please.
Yeah. Cool. Hi. Yeah. Is it okay? Great. Hi again. So now we'll present you FuzzQ, that is a testing method for quantum simulators. We had a great introduction of quantum simulators right now. But it's using a mix between some fuzzing techniques and some more formal method techniques. And so I guess many of you would be familiar with fuzzing, but just a quick introduction. It involves a system under test, so now it would be a quantum simulator, and some kind of fuzzing engine that would basically throw random programs very fast to this system under test to trigger some unexpected behavior. And actually I think a year or so ago, in a very small challenge track that we implemented very quickly, we managed to find many bugs on the biggest simulators just with a very small fuzzing campaign. So we thought that there might be something to investigate here. And so we had an introduction of quantum simulators, but that's an example of a very simple program running in the two most famous simulators from IBM and Google that is implementing the same quantum circuit that should behave the same then. And the only thing you have to know about what this does is that it's a succession of rotation on a qubit, and some of the gates have correlating between two qubits. But I think, like from the other talks, you had a good introduction to what it should mean. And so the reason why we want to test those simulators is because we have to trust them for many tasks, as we saw in the previous talk. And because hardware is very expensive, if you send, there is some available hardware online, but if you send some kind of bigger circuits, it can cost dozens and dozens of dollars for a few minutes of computation. So for education, academy, and even industry, many tasks are based on simulators. And it's also currently the only way to have a noiseless computation. But when we talk about testing, there is always this trade-off between scalability and rigor. So I talked about something that is very scalable and very fast, but not very rigorous. And formal methods would typically scale exponentially with the scale of the system. And so this is a validation gap that we try to tackle, and this is a happy FuzzQ. So I will quickly go through the methodology that we used, but I'll invite you to go through the paper for more details. But basically, we are defining some specs of the some quantum specification that should be verified by all the circuits to build some kind of a formal model that we then parse into a more regular fuzzing campaign, and that we send, and all the circuits that are simulated are sent parallelly into two different circuits, and then we have a novel way of checking equivalence that we'll define afterwards, that we'll get into more depth afterwards. And this should, so the two simulators should give the same answer basically. So if it doesn't, we actually go through it and either update the formal method, the formal model, or report a bug and then go through the loop again. So the main thing that you should remember from this slide is that in the loop we have both some formal model that is built by a quantum experts, and some more traditional fuzzing campaign. And I'll let Vasilis go through, explain you a bit more about the way we check equivalence of circuits.
Hi everyone, I'm going to provide some insights on the oracles that we are using and some results that we found. So one aspect here, if you noticed here, we are using here differential testing fuzzing, okay? Which means you might wonder what do we compare in this differential testing aspect of our framework. So first we do a gate-by-gate intermediate state vector comparison. So we do this so that we can just check whether there is some gate which might cause a divergence in the circuit. Okay. And second, we compare the final output of the measurement. So we measure the circuit, and then it will collapse to some state. Okay. And then we measure, so we want it here to validate the probabilistic nature of the quantum, basically. However, we observed that these two oracles, these two criteria, were not enough for finding all, so some bugs just went undetectable. And this is one silly example. So if you, this is a C-note circuit here. If you try to provide as an input here 0, 0, for example, for Qiskit, you will get 0, 0. And if you try the same thing for a circuit, but what you think it's the same circuit, however, there is a subtle bug here. The developer swapped here the control with the target by mistake. But still, if you provide here 0, 0, you will get still 0, 0. By using the criteria, state vectors, gate by gate, intermediate state vector comparison, you will, this bug of just swapping the target with the control will go undetectable. And that's why we came up with one more oracle. So on top of the state by state intermediate state vector comparison, we extracted the unitary matrices for both circuits. This is just a silly example between two. This can be generalized to multiple simulators. Again, we have provided already the formalism in the paper and proofs that establishes this idea. So we extract the unitary matrix from both simulators, and then we perform this fancy check here, and we should find some kind of identity matrix as a result. And if you now come back to the example that we saw earlier, and if we perform now this oracle, new oracle, you will see that the result here is not the identity matrix, which means that we have spotted a bug using this oracle. So just we used a kind of multi-layered oracles so that we can spot different bugs that might expose in different contexts. Now, you might wonder how good are our tests. Firstly, in terms of throughput generation, test case generations, this is quite fast. We are using Alloy modeling language, which is a dedicated specification modeling language. It's quite lightweight and intuitive modeling language, and it generates quite fast test cases. So this is just a number metric, 140 circuits per second, but yeah, we generated millions of test cases without any issue. So there is no issue in terms of bottleneck here in this aspect. And in terms of diversity, just we took a sample, a good sample, and we noticed that we had a high coverage, so almost all the gates that we modeled in the Alloy model were used in this sample that we checked here. And almost 90% of all the circuits generated in this sample were almost unique circuit structures. Okay, so we had quite a colorful, let's say, sample of examples in this. Now, in terms of the code coverage for circuit, and we performed some experiments, circuit and Qiskit as well, and we noticed that we achieved quite good coverage just with up to 6 qubits. So we achieved this kind of saturation, so no more than 6 qubits were necessary just to penetrate more the code space of the either Qiskit or Cirq simulators. Okay, and we achieved the third oracle that I mentioned earlier, which is about extracting the unitary matrix. It's quite expensive oracle, okay, because yeah, the unitary matrix scales exponentially, and we achieved it did okay-ish up to 12, 15 qubits, okay, but more than 15 qubits, then we are thinking now some other cool ideas that we have already submitted for tackling much more qubits testing. But since we achieved such a nice, let's say, coverage for up to 8 qubits, we were quite happy with the oracle, which already covered the 15 up to 15 qubits. Now let me just show you a small bug, a silly bug. It might seem silly, but it's quite counterintuitive in terms of user expectation. So imagine we have this circuit here. Okay, we have an X gate, and then we have a swap between these 2 qubits. Now, just think on 2 levels. We have the virtual qubits, the Q0 and Q1, the ones that the developers use to write their program. And we have the so-called physical qubits, which are the physical components in the simulator's memory. Okay, you can think of them like the wires here that you can see here. So we have the virtual qubits, labels, okay, and we have the wires, the component, the physical qubits here. And if you try now provide as an input 0, 0 here, it's straightforward. You will compute that the output would be something like that here. So just we flipping a bit here and swapping the 2 wires between them, okay? When we tried this circuit with the differential testing, we noticed that the output is not quite what you see here. And the reason for that, after we discussed this with the guys experts from Qiskit, they told us that the reason behind that is that while they initially provide a mapping like that, so like the previous one, so initially the mapping was like that, so the virtual qubit Q0 maps to the wire, the top wire, and the Q1 to the bottom wire here. But as we perform, after we performing the X gate here, for the swapping story here, then what Qiskit does in order to be efficient, they just doing a remapping, which means that Q0 now is mapped to the wire on top, and the Q1 now is mapped to the other wire. So in order to perform swapping, they do not swap the bits across the wires. They just do this kind of remapping in order to be efficient from memory consumption point of view. Okay, and this is quite, we discussed with them, this is quite, from a user expectation point of view, this is counterintuitive behavior. You wouldn't never expect to see the output. And yeah, this is a very small, silly, might seem a bug, but it's quite something that you would not expect. Now, in terms of, this is just a representation of the memory consumption. Okay, the blue ones is Qiskit, and you will see how amazingly they are doing here. So while you are just increasing the number of qubits and the depth, you will see that the memory consumption is almost flat. Okay, it's not increasing. Okay, whereas with the Cirq here, with the red dots here, you will see that it's being increasingly systematically while we are increasing the number of qubits. And after discussing again with the experts from Qiskit, we discovered that this aggressive, let's say, strategy of Qiskit relies on the concept of the so-called, they are prioritizing the optimization of the so-called happy paths. Okay, they are expecting that all the input that you provide to the program is correct. Okay, for example, we tried providing as angles or silly inputs, for example, negative numbers or silly Unicodes, okay, and the simulator either crashed or just provided some very weird output. We discussed with them and they told us that, okay, you have to check to use some kind of static analysis tool so that you can prevent submitting weird inputs to the angles or indexes, negative numbers. So, whereas SUC is dealing implicitly with such kind of wrong inputs, undocumented inputs, and so on. So that's why the reason behind this amazing performance in terms of memory consumptions for Qiskit. So the main idea of our framework is we are using multiple layers of validation. Differential testing is one of them, the most important. We are using property invariant-based checks, validation as well, so that we can just exhibit different aspects of from different kind of bugs. And the main idea, the main highlight of our framework is that we are pulling the rigor from the formal methods into the amazing scalable world of fuzzing, okay, so that we can achieve more, detect more bugs. And we did discover a couple of bugs, just I presented here some very simple examples so that we can understand better what's going on. But we have just listed some cool bugs in the paper. You can have a look and see what's going on exactly with the simulators. Yeah, more or less this is what I wanted to share in terms of our questions.
Thank you. Okay, questions?
Hi, I was wondering, when you said you compare the state vectors between the simulators at each step, is that's effectively some sort of instrumentation? Does adding this instrumentation change the way the simulator works? Does it prevent the simulator from reordering gates, for example?
No, we didn't observe such kind. Just checking the state vectors?
Adding the operations for extracting the state vectors, does that change the behavior of the simulator?
No, we didn't observe such. No.
So, okay, thank you.
But you don't have to do it at the same step, yeah? Because you sample a lot.
Well, so Qiskit does gate fusion, which might be blocked if you have the extract state vector instruction every.
Measure and then continue with the same.
Measurement is done in the end of the, so intermediate measurement we do not perform.
Thank you.
Oh, that would be a good challenge to extend the
framework. Yeah, this was something that we discussed whether we should provide measurement intermediately, which, yeah.
Even if you do intermediate measurement, you can just drop it. You know, you can play with the circuit. And once you decide it's too dirty to continue the testing, we drop it and restart.
Yeah, but we already had these findings without doing such kind of complex. So we thought that we would share this.
Very good. Other questions?
And if you might wonder something, I'm just making the questions now.
I'd like to know, to find all the bugs that you found, how big of a circuit did you need eventually to find what?
We have this limitation of the third oracle up to 15 qubits.
15 qubits.
Okay, because extracting the unitary matrix is very expensive.
And
so
how many gates?
And
how many gates for 15 qubits?
How many?
Gates.
So the depth, it was up to, we tried up to 200 gates, so the number of gates, it was not an issue, it was the qubits.
Yeah.
And if you might wonder why we focused only on the pure states, okay? Mixed state is something that we are working on. We have some cool ideas and we have submitted some work as well. But since we found this is a baseline with pure state, since we found already something with pure state, we thought we would share with the community, and then we move on with mixed state, where we are expecting to find much more fancy bugs.
Good, very good. Thank you again.
Okay. So who's... Okay. So you do the second part,
I'm the
right?
second.
So do you want to wire him up already?
Maybe later, I think.
Later? Okay, if you want.
Yeah, I just try minutes ago I did it or something. Yeah. Oh, Melania? Maybe I instead use this. Mm-hmm. Yeah. Okay. Okay. Sure.
So I think we're close enough to 1:45 now. So I'm Peter Thiemann, I'm chairing this session, and I'd like to welcome you to the first talk here, which is about adaptive shielding via parametric safety proofs. And you are...
I'm Yao Feng, the first.
Yao is giving the talk, please.
Hi everyone, my name is Yao Feng, and my talk is about adaptive shielding via parametric safety proofs. And the QR code is our paper. So for the motivation part, the problem we want to study is that we want to deploy cyber-physical systems in partially unknown environments. We can look at the example first. So there is a train braking control system. So we want the train to stop near the obstacle, but we cannot crash into the obstacle. And there's uncertainty about the track incline. It means that if we intend to apply an acceleration, there is some unknown offsets, and we cannot directly determine it, and we need to measure maybe when we're doing interactions with the environment. So in this case, we have to use learning-enabled controllers, which means we gather information during our interactions with the environment, while we can still ensure the safety of the system. If we do not use learning-enabled controllers, for example, we use totally fixed controllers, in that ways we have to be very conservative because we do not know the environment and the controller cannot update itself. In that case, the controller is overly conservative, and it will sacrifice a lot of the performance. Before we go too deep into this problem, we can revisit static shielding via formal methods. So as a starting point, we can assume that the train braking system, there's no uncertainty. We know the incline. We know our acceleration for sure. So in this case, we can just use a static formula. We prove the core formula here. So the formula is that it means that under a certain initial condition, under any executions of our controller and the environment evolution, the safety condition is always satisfied. So if this formula is proved, then we can just apply the controller defined by the control to guarantee safety during the training and testing. So we can also write it more formally using some formal techniques. So we introduce hybrid programs. So it is expressed in differential dynamic logic. So there are four basic syntax. So we can do assignment, we can check a formula, also we can follow the differential equation. also, we can compose several hybrid programs into a new hybrid program. For example, we can non-deterministically run a hybrid program, or we can use like a sequential run. Also, there are some loops. So with such like DL tools, we can formally write the train braking system. So for simplicity, we assume that during each control interval, the train only has a binary action space. That is, it can accelerate with a given acceleration A or brake with a acceleration minus B. So there are only two choices. And the core part is that we need to find a control. So here the control, it basically means that we can always brake, that is A minus equal to minus B. And if we want to accelerate, we need to check this condition. And this condition, it basically means that we have to check the braking distance under the next control cycle. If the braking distance is like large enough, we can accelerate in this control cycle. Once we find such a control, we can just follow the shell derived from it. And in this case, it can guarantee safety both during training and testing. And the safe condition here is that we do not exceed the obstacle, and the planned part is just about we move according to the acceleration we just selected. However, as I just said before, static shielding is not sufficient for partially known environments. So if the environment is not fully known and we only afford to do static shielding, we have to consider the worst case to guarantee safety. So this sacrifices the performance. However, if we want to do adaptive shielding, there is also a lot of challenges. So we need to express the uncertainty in the environment, and we also need to define how we adaptively update our controllers. Also, we need to guarantee safety for sure, and also there's some runtime efficiency considerations. Our solution is that we have a programming language framework, so it is expressive, and the experts can specify adaptive shells. And the adaptive shells, at the beginning, it may be also conservative because we do not know about the environment, but it can become increasingly permissive as we get more information from the environment. So here is the overview part. So this is a programming language framework. We need human experts. They define the shell specifications in our language. And we have compilers to compile it into proof obligations and also reinforcement learning trainers. So for the proof obligations, these are like offline obligations. We do not need any runtime verification. And for our adaptive shell, so it contains two parts. So the controller monitor, it is just correspond to the control we said before. It will replace unsafe actions by the fallback action. And the inference module, it will update the controller. So here the main difference between our controller and the previous controller is that our controller is parameterized. So there's a parameter controlling its maybe conservativeness, and the inference module updates such parameter in a formal way. And how we update it is that we collect information, that is observations from the interactions with the environment, and we use that information to update the controller. So we can look at about more details about the updates. So additionally, the agent, the reinforcement learning agent, it needs to learn inference policy. It can be learnable or it can be fixed. So the inference policy, it needs to determine the observations, so what observations we are going to use, and how many budget can we use for each observation. So the budget is the significance level. So we consider there are some randomness in the environment. So if we use these observations, we have to leave for some significance level to give some probabilistic bounds. And after the inference policy, it passes information to the inference module, and the inference module will handle the rest of the problem. That is, doing sound statistical inference and update the controller parameters. Also, we can look at the training example. So here is an visualization of one episode. So the dots here means the position of the train over time. We can see that it moves closer and closer to the obstacle, and it finally stops near it, but do not crash into it. So the blue color means it chooses to brake, and the red color means it chooses to accelerate. And the vertical lines are the braking distance if it chooses acceleration this time. And there are some green circles. A green circle means that it spends some budget to do statistical inference. In this way, it can update its controller, and the controller can be less conservative. And the effect of such updates are shown in green vertical lines. So we can see that once we perform an statistical inference, the braking distance will be reduced. And now we can look at the shell specifications corresponding to such problem. Here are some assumptions. We assume that the effect of the unknown incline is an unknown function f. It depends on the current position, and we assume it is bounded and k-Lipschitz. And then we choose to use a parameter f bar to estimate its upper bound. And for the controller part, the controller is dependent on the f bar, and but the design is kind of similar to the static shielding case. That is, we can only accelerate when certain conditions are correct. And also the environment ensures that the train can always stop, considering the worst case scenario. And there are also relevant proof applications. And also there are some inference part. So we get noisy observations of fx. So there's a Gaussian noise. And the inference part, the user defines how we do inference. So we use the boundedness condition, the Lipschitz condition, and also the observations omega to update our estimates of the upper bound. And also there are some relevant proof obligations to check whether these inference strategies, they are sound. So totally there are these proof obligations, and most of them can be checked automatically, and only one, the red one, we have to assist the automatic provers. So there are some results. So we can see the adaptive is our method. So relevant regarding the unshielded case, we do not crash during training and testing, but we also do not sacrifice the return. So we are very close to the unshielded case. And for the non-adaptive, that is static shielding, in that case, the return is sacrificed. And also the overhead is very low. It is within 15%. So that is the conclusion. We have a programming language framework, and we can specify the specifications. And are there any problems?
Thank you. Other questions? So can you say something about the other use cases that you looked at?
Yes, although we do not present it here, we have a robot like crossing the river, so that is also a use case. So the robot it needs to cross the river over a bridge, but it doesn't know where the bridge is. So it needs to collect information about the position of the bridge, and then it can successfully cross the bridge.
But there was still a zero possibility that you would crash after training, right? Did I get that right? So in the last column?
Yeah, there's zero possibility, but the probability can be specified before training.
I see, okay.
Yeah.
Well, thank you again.
Thank you.
So we have like 1 minute slack.
Sure. Yeah. Shall I begin?
Hmm?
Shall I start? Or
No, we need to wait. Maybe someone falls from the air.
Oh, fair
Right.
enough, yeah.
Feels weird, but okay. Guess we're close enough. So the next talk is on certified decision procedures for width-independent bit vector predicates, and the presentation is by Siddharth Bhatt, right?
Yeah. No. Let's just try. Yeah. Hello. Is the audio working? Yeah. How about now? Okay, amazing. Yeah, so hey everyone, I'm Siddharth, and yes, I'll be talking to you about a fairly long title, which is indeed about decision procedures for bit vectors whose widths are arbitrary. So yeah, let's begin. But first, these are my lovely co-authors. There's Leo, there's Chris, and there's Tobias, and it's been a lot of fun writing the paper with them. And so, yeah. Right. So maybe to set some context, right? Like, why do we care about this stuff? So essentially, the area that I work in is compiler verification, and we're interested to know, are these two programs equivalent, right? Do they have the same semantics? So, what the source program, it divides by 8192, and the target program, it shifts right by 13. So if you remember your powers of 2 to the 13 is 8192, so these two programs do indeed compute the same value. But, how would you verify this if you're an LLVM developer, for example? What you'll do really is to just invoke a tool called Alive, which is written by, actually, some of the people are actually attending here. I've seen Nuno here for sure. And yeah, so Alive is a really nice tool where you feed it the source and target program, and then Alive tells you, hey, look, this transformation seems to be correct. Like this is in fact a legit transformation to do. Now let's suppose instead you screwed up and you wrote a compiler pass that converts division by 1 into shift right by 13. This is of course wrong. And if you ask Alive this, Alive will indeed say that, hey, this looks illegal. It says, on this input, which is when you give it as input 1, the source program produces as output 1, and the target program produces as output 0, right? And so, this is super fantastic, right? Because when you're developing a compiler, a large portion of the compiler's optimizer has these peephole rewrites. So it's really important to get them right. And essentially, Alive is used pervasively within LLVM development. So quite a few of the commits, or most of the commits to the sort of peephole optimizer in LLVM just reference the corresponding Alive proof. This is not cherry picked, by the way. If you just go to the GitHub repo and you search for Alive, you'll basically find hundreds to thousands of commits that do this. Yeah, so that's really awesome. So how does Alive work? Well, roughly speaking, here's what it does. So it takes the two source and target programs, it converts them to a query to an SMT solver. If you've never seen this before, you can essentially think of this as some kind of logical language where the logical language knows about bit vectors. And it then ships this off to a solver, and it asks the solver, hey solver, you have these two functions called source and target. Do they always have the same output for all inputs? And I'm not going to really focus much on the translation from LLVM to the bit vector land. That in itself is fairly complicated because LLVM has crazy semantics about these things called undefined person. But instead, I'm mostly going to focus on how the solver actually solves this problem, right? So I'm going to focus on the latter part of the translation for today's talk. Right, but the solver really is a genie, right? In that, it's you ask it, hey, is this true? And it sort of tells you, right? So that's amazing. But I have one problem with this, which is it's kind of unfortunate that I need to say 32, right? Because this particular transformation that I have, it's legal really for any width that I want. So I really want to say, hey, please give me a symbolic width, and for this symbolic width, can you sort of verify this transformation, right? So sort of we want to take this bit vector solver that we have, and we want it to be a PBV solver, which is a parametric bit vector solver, or a width independent bit vector solver. So that's kind of the goal of this talk. We want to have a solver for bit vectors, but which not only reasons about a fixed width, which you can always convert into a SAT problem, but you want something that can reason about this parametric width as well. So sort of in our, like in our implementation, we provide these two tactics within Lean. One is called BV Automata, which is a solver for this thing, which uses automata theory. It's complete for a large fragment of bit vectors. And then we have another solver called BV MBA, which uses some algorithm that I will explain, which is cute. It's very fast, but it's only sound and complete for a much smaller fragment of bit vector problems. And of course, all of this is mechanized in Lean, so it's all available as tactics that you can use. Also, it's open source, and if you want to use the tactic, you can take a screenshot and you can include that link into your Lake file. So if you want to use the tactics, then that's how you use it. Right. So I'll now sort of get into the actual algorithms and like how the sort of tactic works, and a little bit into the hard parts during mechanization. Right. So to set the stage, let's suppose we're trying to prove that bitwise AND is idempotent, which we know it is, and that's how you'd actually invoke our tactic. You'd say by BV automata, and then it gets proven. So okay, what does the tactic do? What does the actual decision procedure do? So the idea is, well, okay, we are trying to prove this identity for all possible widths. So we might as well imagine that the bit vector has infinite width, right? Because if you want to prove something for width 1 and width 2 for width 3, you might as well think to yourself, well, maybe I just prove it for the infinite width case, right? So now we have these two infinite streams, both of x and x, and then we look at x bitwise and x. So that gives us x0 and x0 at the first location, and then we try to check whether at that particular location x and x equals x, which it does, which you can sort of check by exhaustive enumeration. Okay, so at least for the first bit, we've established that the predicate we want to check is true. Great, then we progress to the second bit, where we again get the same kind of obligation, right? And then we again check that it's true. And so we can sort of keep going. So then what we've done is we've converted the question of checking that predicate for all possible widths into really the question as to whether does this predicate, when interpreted as a bitwise predicate, produce an infinite sequence of true, right? So that's sort of our reduction from this universally quantified bit vector thing into a bit stream semantics. So that's our first reduction. Now the second reduction is we take these bit stream semantics and we instead interpret them as automata. So let's maybe take a brief look at how we do this for bitwise AND. So let's suppose in our inputs, the input A has value 0 and the input B has value 1. Well, then the output needs to be 0, right? So that's what's written on the transition label there. These are finite state transducers, so they take two inputs and they produce one output. And then similarly we can sort of keep going. If the input is 1 and 1, then the output is 1, and if the input is 1 and 0, the output is 0, and so on, right? I think you see how it goes. So the transitions are labeled, and so when we transition, we label them by the output as well. So this automata essentially completely captures the behavior of bitwise AND given the input bits. So then the other operation that we need in order to verify x and x equals x is we then have an automata for the reading an input itself. So that automata is really simple. When it reads an input 1, it produces an output 1. And when it reads an input 0, it produces an output 0. And then what we do is we compose the two automata together. So like you can compose finite automata together, where you can say please take the input of this automata from this other automata. So we then compose the automata to get an automata for x bitwise and x, which you get by composing the a bitwise and b automata with the x automata. Cool. Now the next thing we need to be able to decide is equality of bit vectors. So for this we need a slightly more complex automaton, which I'll walk you through. So the idea is, well, we start with the state where we assume that things are good and that the bit vectors are equal, And now when we see the 2 bits are equal, we say true. And then we get the next 2 bits, which are maybe 0 and 0. We learn that it's true. But now what we see is we see a disagreement. A is 0 and B is 1. So we then output false and we transition to a sync state. Now the sync state will essentially always output false. And this is important, right? Because it's like once you know that at some width the bit vectors have begun to disagree, you then know that they will forever disagree for any extension. So that lets you transition to this state where you now always produce false. So it's like at this point we really have all the automata we need for the original predicate we were trying to decide for x and x, for equals and x. So we again play the same trick. We compose the automata into like the final automata we need, and that's what the automata looks like. And then we go back and we ask the question, right? Does this automata always produce true? Now we know by visual inspection that clearly the automata always produces true because there's no transition into the state that produces false. So in this case we can say yes, this automata does always produce true. And now sort of popping the stack a bit, well, what does this imply? This implies that the bit stream is always going to be true, but that essentially implies that the original goal that we were trying to prove is in fact true. So that's sort of the full sequence of reductions that we perform in order to prove what we were interested in. But I cheated a bit, right? Like here I said, yeah, okay, just look at the automata and clearly it's true. But how do you actually convince a proof assistant of this? So essentially we have 2 different backends in order to do this. So we have one backend that does this based on symbolic model checking. So we use k-induction to do this, where we encode the automata as a SAT problem and we check for like that all reachable states are good. And we have another backend that's based on automatic structures, where we have a library for building NFAs, and yeah, like we do sort of automata minimization and then emptiness checking of the language to determine these. Yeah, and both of these are mechanized. So then it's like, yeah, we can sort of like see that even operations like addition can also be encoded in this framework, right? You maintain one state, which is your carry, and that tells you what you need to do. And then similarly, in the exact same way we encoded bitwise and, we can also encode predicates, right? Like we can take the conjunction of predicates and we can take the disjunction of predicates and so on in the same way. So basically a lot of stuff is automata representable in that like the full linear fragment along with Boolean combinations of predicates and things like this. Right. So then let me explain the second algorithm, which works on a fragment called mixed Boolean arithmetic. So this fragment has on the inside bitwise terms and on the outside linear arithmetic terms. So it's a stratified syntax. So that's the sort of formal syntax, but I think you get the idea. So the way we actually prove this is we first show that this relation holds for bitvec 1. So what I mean by that is when we substitute 0, 0, it evaluates to 0. When we substitute 1, 0, it evaluates to 0. Similarly for 0, 1. And crucially for 1, 1, we get 1 plus 1 minus 2. So this algebra is happening over the integers, not on the booleans. So once we know this fact, we can then lift it to any number of bits we want. Because if we take a 2-bit number and we interpret that number over the integers, what we wind up getting is this kind of expression, where x1, x0 as bits becomes 2x1 plus x0 as integers. And so then we can grab all the first place digits, rearrange the terms, which is equal to 0 by the theorem we proved before. And then we can also grab the lower bits, which is once again equal to 0 by the theorem we proved above. So this somehow lets us lift the result in bitvec 1 to any bitvec w. How well do these solvers do? Well, we tested it on 2 problem sets. So one is on this MBA BLAST problem set that comes from deobfuscation. So as you can see, the sort of the MBA solver, which is specialized, like is really good on this data set. And yeah, the automata solver solves all of them. The k-induction solver solves up to 1500, and after that the sort of how do you say, the SAT formulae get really large, so it times out. In terms of compiler verification, we take the rewrites from LLVM, and essentially, like on the 8,000 problems, we can solve something like 2,300 of them. Of the ones that we don't, it's either because these rewrites in LLVM are fixed to 64-bit, so they involve numeric constants that we need to first generalize, which we haven't done yet. And also there are some rewrites which involve multiple widths and 0 and sign extents between these widths, but our solver assumes that everything has the same width. And finally, there are rewrites that are just outside of our fragment because they involve operations like multiplication and division and so on. But yeah, so I guess that's what I'd like to say. If you can use our solvers to trust your rewrites with formally verified solvers. So I can promise our solvers has no bugs because it's written in Lean, and it's pretty fast as well. And so yeah, there's the Git URL to actually grab the solver. And finally, I'm trying to figure out what I do with my life after my PhD. So if you have advice or positions, please hit me up. Thank you. Yeah.
Please, question.
Thanks for the really interesting talk. One thing that these kind of automative-based solvers can do that is deal with quantifier alternation. And so I'm curious if you've seen any examples like an LVM where quantifier alternation might actually be useful, or is it just generally what we care about really is just for all statements?
Yeah, so that's a good question. So like there's a paper from last year called Hydra, where the idea is that they take a bit vector rewrite that involves 64 bits and then try to shrink it down to like 4 bits. This is like a step that you need to do in their larger algorithm. And to do this, you need an exists for all quantifier alternation. So that like it is in fact useful. And yeah, you're right that we could in fact do quantifier elimination within our thing, although we haven't implemented it yet. But that's one use case where it would genuinely be useful. Yeah.
Cool. Thanks so much.
Yeah. Yeah.
What would be the sort of use case for bit vector problems that would need those criteria? What would they look like?
Sorry, could you clarify? Like
what are some examples of bit vector problems where you would reduce it down to, let's say, intersection of symbolic finite automata with numeric types?
So maybe this wasn't really clear, but in some sense it's like the way in which we sort of handle the Boolean fragment, like the full predicate combination, is by building individual automata for each of the atomic predicates and then combining them symbolically with sort of intersection and union of the languages. So we somehow like fundamentally make use of the fact that regular languages are closed under complementation and intersection and union. Yeah, exactly. Yeah.
Okay. Maybe I can ask you offline.
Yeah, that's,
okay,
that's what I wanted to suggest.
Yeah.
All right. Well, thank you again.
Oh, thank you.
And we're moving on to the next presentation. That's on checking delta satisfiability of reals with integrals. And yeah, he doesn't have a name tag, sorry, but.
Sorry about it. How to?
Okay, so finally checking delta satisfiability of reals with integrals, and the talk is by Vishnu. Please.
Thank you. Hi everyone, I'm Vishnu. Today I'm going to talk about checking delta satisfiability of reals with integral. This is joint work with Cody, Rohit and Prasad and Mahesh. I would like to, before starting my talk, I would like to shout out to our first author, Cody. He is listening to us remotely. He could not come here, but despite being too late in US, he is listening to us. And Our goal in this project is to extend the delta decision procedure to reason about formula that includes integrals. So why it matters, like why we need integrals? So many verification and synthesis tasks can be reduced to naturally to that involves integrals. So for example, if we consider the problem of verifying fairness of hiring algorithm shown in the right, where ethnicity greater than 10 means like a minority group. So to verify fairness, we have to check the probability of being hired given the minority status over the probability of hiring given non-minority status should be bounded by 1 minus epsilon. So this kind of probability, which involves Gaussian, will boil down to the formulas which have integrals. And to check this kind of formulas, there is no existing tool to solve it. So that motivates us to build a new tool. So we want to do this by extending the delta decision procedure. So now let me jump into what is delta decision procedure. So it's a key idea introduced by Gio et al. In 2012. Basically, the idea here is it provides the framework that approximately decide the formula over a real number with a small tolerance are satisfiable, delta satisfiable or not. So if we have the formula phi which is over real, if we feed to the delta decision procedure, output will be onsat, which means formula is unsatisfiable, or it will be delta sat. Basically, delta sat means a delta weakened version of formula is satisfiable. So mathematically, like it is done that way. I have put original formula and the delta weakened version. So interestingly, formula can be onsat and delta sat at the same time. This is by design. That basically means the relaxed version, little relaxed version is delta satisfiable, but the exact one is onsat. So, and this framework support any computable real function such as sine, cos, log, or exponential. So this gives a way to solve integrals in a promising way. Now, after talking about delta decision procedure, let me talk about our contribution. So our contribution are on threefold. First, we created the logic alint which support nested integral with variable bound. And after that, we proved disability of delta satisfiability for this logic. And finally, we implemented the tool called INDREAL, which basically support integral reasoning and can solve the problem I showed at the beginning. So now let me formalize the problem. So basically, what we want to do is we want to check the formula phi in the quantifier free first order logic over the real is delta satisfiable or not. What does it mean? Like what is new in term of terms? If you see like that's highlighted term, the integral is the new one, new addition to the logic, and it has the variable inside integrants and the variable bound. It support variable bound also. So essentially, we are asking, can we decide delta satisfiability when the formula involves integral? In order to solve this, we combine SAT solver with the theory solver. This combination is what leads us to our new tool, INDREAL. So for doing that, we have to, before diving deep what we made changes in the existing DREAL, we need to learn about interval constraint propagation. So the core of delta decision procedure relies on interval constraint propagation. So basically, it sorts for the delta with box that satisfy all conditions. For doing it, it uses two operations. One is branching, basically it's naive way of splitting the boxes, and another is pruning. The pruning basically means we shrinks the size, the interval of box using the function property. The next immediate challenge is how we can prune efficiently when the integrals are involved. So basically the DReal tool, which is the foundation for our work, uses SC4 revised algorithm to prune. So basically it has two parts. One is forward evaluation, which means computing the sound interval enclosures, and second is backward evaluation, computing the smallest smallest input interval which output intersect with the output interval. So we extend forward evaluation for supporting integral using ARB, integral enclosure using ARB. Later after this I will talk about ARB, but ARB basically is the library that support integration. So and we made change and we came up with the new technique for backward evaluation. Basically technique is we estimate how much each input variable contributes to the output, and we repeatedly shrink the interval using binary search. So we use ARB for integration. So it's a library which represent values as a ball. So ball basically means there will be midpoint, and there M is the midpoint and the R is the error radius, and this provide rigorous numerical enclosure, and it provide integration procedure over arbitrary complex ball functions. So it uses algorithm that quickly converts on piecewise homomorphic function, and in our case we use like conservative estimation in our tool, so we can know our answer are safe. And basically we also convert between balls and interval. So basically we do that. I will talk about that in the next slide. This is overall architecture of our tool. So we use like a DReal uses something called IBEX. IBEX is an open source library for constraint solving of real. So it uses interval, but ARB use ball, so we do interchange between ball and interval in our tool. And basically we added the parser to support the logic, and in forward propagation it invokes ARB for computing integral enclosure, and in backward propagation it implements a binary search routine to do backward propagation. So that's overall architecture of our tool, and our tool is available on GitHub, and please download and use it for the problem which involves integrals. And now let me talk about the overall evaluation of our tool. So for evaluating tool, we created the suite of benchmark which consists of 41 benchmark, and it involves privacy problems, fairness problem, and the synthesis problem. So and our tool can handle a universal and existential quantifier, and we are often faster than Mathematica, which is industrial tool for doing this kind of thing. We only lose in triple integral case. Beside that, we almost always perform very good. If you see the speed factor, we almost always do reasonably well compared to Mathematica, and it is open source. And our result, despite being like a approximate decision procedure, our results are identical to exact satisfiability. And we have also a broader scope. Basically, most of the example we coded with the quantified alternation, Mathematica wasn't able to solve it. So our tool provides the broader scope. So now the next question clicks in the mind is how scalable is our tool? So because we can perform faster than Mathematica, and it is scalable? So for testing that, we created suite of example where we have the sum of nested integral. So we went up to 100, and we can do that in 0.02 seconds. So if there are 100 continuous sum of nested integral, we can do that in relatively very minimal time. And another set of benchmark we use is product of nested integral. For doing that, our tool took 0.6 seconds when we reach 100. So in conclusion, the delta decision procedure provide a promising way to solve formulas with integral, and we were able to realize this by implementing the DReal tool, and we were able to solve many privacy and fairness problem. For us, the next step is to, as I said previously, like for triple integral case, our tool doesn't perform well enough, so we want to optimize for higher dimensional integral. We want to optimize that. Next thing, we want to support a partial derivative, and also we like to build some domain-specific tool, verification tool on top of DReal. Thank you.
Can you get set up? So we would have time for one question, but yeah, go for it quickly, please.
You mentioned quantifier alternation. So can you say, like, is that coming from DReal, or did you have to do something to support that? Is it decidable? Can you speak more about the for all exists?
So it is decidable, and basically we built on top of DReal, so that's what comes with DReal also.
Okay.
So, but we did for the integral part.
Cool, thanks.
Thank you.
Thank you again. So next talk is on co-inductive proofs of regular expression equivalence in zero knowledge. And the talk is given by John.
Yes.
Please.
Nice. Thank you for the introduction. My name is John Colasar, and today I'll be giving a presentation on the paper Co-inductive Proofs of Regular Expression Equivalence in Zero Knowledge. We want to have private proofs about regexes because, for instance, we might want to verify a regex-based content filter that's part of some larger system. We might want to filter profanity or spam in messaging apps, or we might want to have a front end for a generative AI system that uses regexes to reject queries that contain specific terms. For instance, if we don't want users to ask sensitive questions about topics like voting, we could pass the user's message through a private filter regex that looks for the words vote and elect. If we get a match on one of those words, we reject the query instead of sending it forward to the rest of the system. Now, the developers of a filter like this would want to keep the filter private to hide potential vulnerabilities if they exist, but for legal reasons, that filter may be required to be at least as restrictive or permissive as some public specification, and an external auditor would need to confirm that. The standard way for that auditing to happen is for the developer simply to hand over the filter directly to the auditor, but that contradicts our goal of keeping the filter private. Fortunately, a better alternative is possible with some techniques from cryptography. With a zero-knowledge proof, the developers would be able to convince the auditor that the filter satisfies the spec without revealing exactly what the filter is. Instead of just giving the filter directly, the developer would provide an obfuscated proof certificate about the filter that doesn't show what the filter is, but provides evidence that it meets the spec. There are other use cases for private regex proofs as well. Network programs use regexes for packet filtering, and on the theoretical side, regex equivalence is a p-space complete problem. So by targeting this, we're the first to target a p-space complete problem in zero knowledge. More specifically, to address the problem, we introduced CRAPE, which stands for Cryptographic Regex Equivalence Proof Engine. CRAPE is a zero-knowledge protocol that lets us prove that two regexes are equivalent. In our setup for the protocol, the prover owns both of those regexes and generates an equivalence proof for them offline, and then sends an obfuscated version of that proof to the verifier, who validates that proof using a custom proof VM. For some background, a zero-knowledge protocol, or ZK protocol for short, is a cryptographic method of communication between two parties known as the prover and the verifier. The prover convinces the verifier that it knows some secret without revealing the evidence for the secret. The quintessential ZK example is the Coke Pepsi taste test, where the prover has some secret knowledge about how to distinguish Coke and Pepsi by taste, and the verifier wants to confirm this. The verifier would fill a cup with either Coke or Pepsi secretly and ask the prover to say what it is. If the prover gives the wrong answer, the verifier knows the prover was lying. But if the prover gives the right answer, and they repeat this process enough times, the verifier eventually becomes convinced. Importantly, the verifier never learns how the prover is doing it, and that's the essence of zero-knowledge proofs. I should mention at this point that I'm using the word proof in two different senses. For our purposes, we want to provide a ZK proof about the existence of a logical proof. When we want to move into the domain of regex equivalences, the proof that we provide is a list of discrete steps where each step in that proof has pointers to the other steps that it uses as premises. And the prover and verifier iterate over this table of proof steps one by one, confirming that every individual step in the proof is valid. And we reveal information about these steps only selectively, so that the verifier can't see the values manipulated by those steps, but can see that the steps are valid. We have three main building blocks for our approach for CRAPE. We have our new proof format for representing these proof certificates. We have a new algorithm for generating the proofs that we validate. And we also have a new proof validator for confirming that proofs are correct on the verifier side. Let's talk about these one by one, starting with the new proof format. We base our proofs on an important observation from prior work, which is that if two regexes agree on the empty string and all of their corresponding derivatives are equal for the whole alphabet, those two regexes themselves must be equal. Now, what exactly are derivatives? Well, if P is a regular expression and C is a character, then the derivative of P with respect to C is the regex that represents the behavior of P after reading C from an input string. For instance, the derivative of AB or AC with respect to A is B or C. The derivative of BC with respect to A is the empty set because BC doesn't accept any strings that start with A. And the derivative of A star with respect to A is just A star because reading one A doesn't limit the number of further A's that we can read. Let's take a look at how we can use these derivatives in action to prove an equivalence between two regexes. Suppose that we want to prove that A star or A star is equivalent to A star. We have only one character for our alphabet, so we have two proof goals. We need to show that these regexes agree on the empty string, which is what this E function represents. And we also need to show that their derivatives with respect to A are equivalent. Both of these regexes accept the empty string, and that takes care of our first proof goal. And for the derivatives, we have A star or A star and A star. These two things aren't identical to each other, so we need to prove separately that they're equivalent. And to do that, we recurse, and we use the same proof strategy again on these new regexes. If we want to prove that A star or A star is equivalent to A star, we again need to show agreement on the empty string and derivative equivalence. They both accept the empty string, and their derivatives are A star or A star and A star. That means that if we want to finish the proof now, we need to show that A star or A star is equivalent to A star. But this is exactly how we started this current step, and that means that we've reached a cycle. This cycle is actually an important part of the proof. We haven't seen any counterexamples on this cycle since all the corresponding regexes have agreed on the empty string, and that means that further repetitions of this cycle won't yield any new counterexamples. And because our alphabet is only one character, the only way to keep exploring forward to see more potential counterexamples is to keep moving along this cycle. So that means we've exhausted the entire possible space of potential counterexamples, so there are no strings on which our two starting regexes can disagree, and that means that they're equivalent. And that's how we finish our proof by co-induction. And to express this kind of reasoning in proofs that we can validate in ZK, we create a custom calculus of logical rules for reasoning about these cyclic patterns in the derivatives of regexes. And you can see some example rules in this table. Now that we've talked about our proof format, let's talk about how we generate proofs in this format. We base our proof generation approach on this regex equivalence algorithm, which comes from prior work. We search the trees of two regexes' corresponding derivatives exhaustively until we find a counterexample or we hit a cycle on every branch. This algorithm is guaranteed to terminate because the derivatives of a regex must fall into a finite number of equivalence classes. That means we're guaranteed to hit a cycle on every branch eventually if there are no counterexamples. We can convert this equivalence checking algorithm into a proof generation algorithm by recording the execution trace of our derivative search and turning that trace into a proof tree and returning that tree as our output instead of just returning a Boolean result. Now let's talk about how we validate these proofs on the verifier's end. When we're validating a proof in ZK, we hide the values manipulated by each proof step to make different uses of the same proof rule indistinguishable from the verifier's perspective. We accomplish this using a standard cryptographic technique known as commitment. That means we map integers to elements of a special finite field such that recovering an integer from its commitment is not computationally feasible. You can think of it as working like a hash function in that regard. Also, when we're validating individual proof steps, we use multiplexing. That means we run multiple rule checking functions on each proof step, only one of which is for that step's real proof rule. And the verifier can't see which of those checkers is the real one, but can see that at least one of them succeeds for a step. And in our implementation, we group our proof rules into 3 categories for multiplexing, where the verifier can see the category of each step's rule, but not the specific rule within that category. Now let's move to talking about our evaluation for CRAPE. We test both our proof generator and our ZK proof validator. To test the proof generator, we attempt to generate equivalence proofs for 7,353 equivalent regex pairs from Flash regex, which is an older tool. Of those pairs, 72 hit our time limit of 10 minutes, but all the others succeed, and you can see the running times on this log scale. After we generate all these proofs, we select the largest ones to use as benchmarks for our ZK proof validator in the next step, along with some random samples from the rest of the collection. You can see the running time statistics for the 2 categories here. In general, the benchmarks that we selected are slower to run than the rest of the benchmarks because we chose the biggest ones according to multiple size metrics. The proof step count statistics follow a similar trend, where the benchmarks that we selected have more proof steps in general. To test our proof validator, we run our ZK proof validator on those proofs that we selected from the first part of our evaluation, and we use multiple different configuration options for it. We use our default settings with the 3 multiplexing categories that I mentioned before. We use no multiplexing, which means the only checker we run on a proof step is the real one. We use full multiplexing, which means we run all checkers on all steps. And we also run it in plain text, which means we disable all ZK operations. No multiplexing is faster than the default but less secure. Full multiplexing is slower and more secure. And plain text is faster by 3 orders of magnitude but provides absolutely no security. The median running time ratio of no multiplexing to the default is 0.74, and the median ratio of full multiplexing to the default is 3.42. That means that with our default settings, we can achieve realistic performance that's comparable to what we get with no multiplexing, while still getting significantly better security than what no multiplexing provides. To conclude now, I'll talk about some related work and potential directions for the future. There are other ZK protocols for validating logical proofs, but none of the older protocols target regex equivalence specifically. They target other formalisms. Also, there are older ZK protocols for reasoning about regexes not inside logical proofs, but they only check membership of individual strings in a regex and not regex equivalence. For some future work, we could improve CRAPE by extending it to handle clean algebra with tests, and also features that are not allowed in pure regexes, like intersections and complements, and back references and look-ahead assertions. We could also move to handling other p-space complete problems in ZK, like NFA equivalence, and of course, performance optimizations are always possible as well. To conclude, our contributions are that we create the first zero-knowledge protocol for validating regex equivalence proofs. We create the first practical ZK protocol designed to target a p-space complete problem. And to support that protocol, we create a new custom calculus of proof rules for expressing proofs about regex equivalence, along with an algorithm that generates proofs in our format. If you want to discuss this with me further, you can reach me at this email address or at my website. I'm on the job market if you want to talk about that. So thank you for coming to my presentation. If you have any questions, I can take them now.
Questions?
Hello, thank you. Is there a particular design choice between using the derivatives and sort of induction type thing versus using like an automata normalization for your proofs? Like, is there a crucial part of that? Is there like an intentional crucial part there?
Yes, it is intentional. If we used proofs based on state machine conversion, we would need to provide evidence of the correctness of our translation of these starting regexes into state machines. And by using derivatives, we're avoiding that layer of indirection. since we're reasoning about regexes directly, so we never need to validate a conversion between two different formats.
Thanks for the talk. Do you think it could be applicable to omega regular expressions? This would be, for example, a good starting point for zero-knowledge model checking evidences.
What do you mean by omega regular expression?
It's essentially you replace the star with a little omega, which means that you can repeat infinitely many times a pattern.
Yeah. Yes, the system would be extensible to that. Now, but is the theory of omega regular expressions decidable?
Yes, it very much is.
So as long as you have a calculus of proof rules for expressing proofs about those omega regular expressions, then you would be able to encode those kinds of proofs in zero knowledge.
Cool.
Brief
yeah.
similar question. If you had considered or looked at regular tree expressions at all, it would be very useful for like XML validation in a zero knowledge way.
Yes, the answer to that is similar. That you would need to make your own theory of proof rules for expressing the certificates.
Sure.
Well, that, as far as I'm aware, that doesn't exist currently. But if it would be possible to create that theory, so then you could do it in zero knowledge.
Thank you.
Well, thank you again. So our next presentation is on incremental certified programming, and the talk is given by Thomas.
Yes.
And I guess we can start, please.
Thank you. Can you hear me? Yes. Okay, good. Okay, yeah, thank you everyone for being here today. My name is Thomas, and I will be presenting our work with Kenji, Nicola, and Eric, where we study how to work incrementally with certified programming. And with certified programming, I mean writing programs and writing their specs, and then proving that these programs are correct, all within the same system. And where one important aspect is that the process of programming and proving is deeply synchronized. So for instance, if we introduce a bug in our code, we know that we can immediately catch it during the proving process. And we cannot prove it because the program doesn't satisfy the specification. Or in the same way, we could, for instance, for any modification that we make in our code, we necessarily need to go and update our proofs because, once again, the programs don't satisfy their specification. And so this synchronization between programming and proving is crucial for certified programming, and it's at least one of the things that differentiate from pen and paper proofs. And there are several systems where we can do this. We have Rock, Lean, Agda, and many others. And so what we were interested in was on how do we build these certified programs? How can we get to this fully defined program and this fully finished proof? Because one alternative could be to just follow a classic traditional kind of waterfall approach where we first define completely our definitions, our program, and only then we go ahead and prove it correct. But we were interested in seeing what happens if we wanted to follow a more agile or incremental approach where we could define our program step by step and leaving parts unimplemented. And so the first question, and of course with that we can do the same with our proofs. And so the first question is how do we define these incomplete programs? And I will be using this whole symbol to refer to unimplemented code. And there are several ways. For instance, we could have axioms. We could have a to-do axiom that inhabits any type, and we just plug it in the hole. We could have monads with specific constructor cases to refer to unimplemented code. We could have exceptions if we had full support, like in any mainstream programming language. And then there are many, many, many other options. And in our work in particular, we explain a little bit more about these different approaches, but we don't specifically focus on this aspect of incremental programming because it shares some concerns with non-certified settings. So instead, we focus more on the proving side of certified programming. And in particular, how do we manage proofs when in the presence of partial programs? Because as soon as we have incomplete programs, we immediately start having issues. And this is mainly because our specifications are designed for the complete versions of our programs, and of course, then they are not valid for intermediate states of development. And so this means that whenever we have a hole in our program, this will eventually show up in the proofs, and of course we will get stuck, and we won't be able to do anything. And so one alternative is to try to circumvent this. The easy way is, for instance, in ROC we could use the admit tactic and just skip the proof and do nothing. But this is effectively breaking this synchronization between program and proving, because now any change in the code is not reflected with a change in the proof. And so the issue is that, for instance, we could introduce bugs and we don't see them reflected in their proofs, among other things. And so what do we do with this issue, and what is it that we really would like to have if we were working incrementally? And I'm gonna do an idealized incremental scenario where we are gonna assume that we fully support this practice, and to see kind of the things that we would like to see have. And so for the scenario, I'm gonna assume that we have some interpretation function that takes some input from some type term, which is some big inductive type, and returns some terms of type val. And we'll assume this is complete for now. And what we actually want to do is define this optimization function, which will start just by putting a hole. We don't know what it's going to do. But the only thing that we do know is that it should preserve the semantics of the interpretation function. And so the first thing that we would like to have is, in the same way that we put a hole in the definition, we kind of would like to just say, oh, this is trivial, there's nothing to do. I haven't done anything with my definition, so QED. And then, of course, because we're in an incremental scenario, we're going to add a little bit of code to our definition. And we would expect that our system will flag this as, hey, the proof is no longer trivial, you have to do something. And sure enough, we did something, so we're going to go ahead and prove it. But the important part is that we only programmed what we needed, and we only proved what we added to the code, and nothing more. Then a second thing is that the proofs should be stable. And by this I mean that, for instance, if we add a second case to our implementation, and we fix the proof, the existing proofs that were before, they should remain valid. We shouldn't need to touch them, and they should remain valid. And of course, again, we should only care about the new code that we added. And also, is that, for instance, what happens if we found that this is not provable, there's some error. The only two options that there should be is, first, that we either introduced a bug, or that the specification was not correct from the beginning. But at no point should we need to fill in the hole, right? The incomplete code should have no effects on the proof that we're doing. And then, so we can continue the process. We can implement each step of the way until we reach our final version of the program, and we prove it correct, and we're happy. And that's the final part of the idealized scenario. And so the question is, how can we do this in a systematic way, and that we actually get our end result, what we wanted, and very importantly, that each step of the way, the programming and proving parts are synchronized. And one thing that we think is crucial is the fact that properties should be incremental. So in the same way that we can code step by step our programs, we should be able to do the same with our proofs, and knowing that they are stable all the way. And this is, of course, not always possible, and we can see it directly with our example here. If I take the definition of the optimization function and put it in the theorem, I get this equality that it's almost always not provable, because it's, of course, interpretation of a whole equals interpretation of some term, and we cannot put it. And more generally, the issue is that equality is not incremental. So the syntactic restriction of propositional equality is too strict, and it doesn't allow for incompleteness. And since equality appears everywhere, there's many properties that are not incremental. And there is an approach that addresses this issue, so it takes incompleteness in consideration. It's basically by reformulating the specification. And this is the approach that the Coq-R project took. It's a mechanism formalization of R. And so what they did, the approach is that they define a result monad, which represents the possible results of the interpreter. And in particular, they said, okay, this whole is going to be this case, this constructor. And then for the specifications, they define this function result prop, which allowed them to specify what property each result should satisfy. And so in particular, they said, okay, the incomplete code is always true. No matter what the specification, it's just true. And so using this function, they can state any theorem, and they know that the incomplete part will be handled automatically, and they don't need to do any admits or anything. So this works. This is great. The only thing is that this is specific to this project and the monadic approach that they used, and that it's manually defined, so it's prone to human errors. And the last thing is that it's only on the conclusion. So the question is, what happens if you are assuming something of an incomplete program and so on. And so we wanted to take this approach and make it more systematic. So this brings us to our work right now, where we present a formal framework to support incremental certified programming by guaranteeing this incrementality of predicates, of properties, by using this reformulation approach. And so the first thing we introduce is a completion refinement relation to relate the different states of the program. We also introduce a notion of completeness to refer to the final state of development. And with this, then we define incrementality simply as monotonicity of reasoning over this refinement relation. And then for the reformulation part, we specify 3 properties that any reformulation should satisfy. The first one is, of course, incrementality, and which gives us the stability of proofs. The second one is recoverability, which says that once you finish your program and you proved your reformulated specification, then it should imply the original one. And this is important because it can happen that you do all the work, you finish, and only at the end you realize that your original specification was not true. So all of your work went to the trash. And in the very silly example, we could have the true predicate, which is incremental, that's great, but of course it doesn't say anything about our original specification. And finally, the third property is approximation, which says that the original predicate should imply the reformulated one. And in essence, what this is saying is that the reformulation process should not introduce any errors. And again, as a silly example, but we could have the false predicate, which allows us to recover the original one, but of course we cannot do anything with it. We cannot prove it. And so if a property satisfies these 3 other properties, then we call it an incremental reformulation. So then what we noticed is that there's a fragment of predicates that can be systematically derived. An incremental reformulation can be systematically derived. And I'm not going to show all of the examples, they are in the paper. But there's 2 things that I do want to emphasize, is that for the process of reformulation, the polarity of the predicate matters. So where you sit in an implication, whether it's on the goal or in the premises, it matters on how you reformulate. And that we add a reformulation for equality using this refinement relation. And so I have a specification here which makes no sense, I don't know what it is, but it's just to show that there's an equality on the premises and in the goal. And when we reformulate, what we do is replace equality with the refinement, but we switch the directions, and we also add some additional predicates. And there's more in the paper. There's also some simplifications that one can do on the reformulations and so on. And so once we had this, we implemented a ROC prototype with type classes, and we did 3 case studies, but I'm only going to show one, which is with ComCert. And what we did was we took the whole compilation pass, we took in specific the deadco elimination pass, and we made it incomplete. We basically took one branch of code and we removed it. And then we were able to still prove the correctness lemma of this pass. And the main takeaways that I want to show in these presentations were that, and that we learned from this case study, were how to reformulate complex inductive predicates, and on how to retrofit incompleteness into an existing project. And we tried, for instance, to follow an monadic approach, but we noticed that it was too costly because we had to change many signatures, and we thought it was too costly. And then what we ended up doing was that we added an extra constructor, but that also ended up being too, it wasn't a good solution because we duplicated a lot of code. And so what we took from this experience was that we needed some lightweight manner of introducing incompleteness into projects, and we think that probably exceptions is a good choice. So we are working towards an exceptional approach to working incrementally in certified programming. And that's it. Thank you very much.
Thank you. Yeah, questions?
Hi, Max New, University of Michigan. So in Agda, using holes, you can put holes in your programs and your proofs. You already get a lot of incrementality.
Yep.
So which of these one of these properties is not satisfied by it?
The thing with Agda is that the holes are basically axioms, and they don't have any computational content. So basically, if you try to prove something about them, and sometimes you get stuck terms.
Okay. Oh, so you want to have like canonicity type thing, even in the presence of the holes.
Yeah.
Okay.
And it's even worse. Oh, sorry, maybe I need to take this. It's worse if you have, for instance, recursion, because then you start getting some weird stuck terms, and then you cannot prove anything. You're back in the same spot as before.
Okay. Yeah. Thank you.
Welcome.
Well, thank you again. All right. So now we're getting to garbage collection, pathological cases for a class of reachability-based garbage collectors. And this presentation is by Matthew Today.
Today, yes, let's say that. I'll ask my dad at some point how he likes pronouncing it. Okay, so I guess we're going to shift gears here a little bit and talk about garbage collections. You're in the proof section. There will be a proof at some point in this paper, so look forward to that. I'll spend a little bit of time here telling you why I care about garbage collection. Well, you know, memory management is a big problem. Anytime you have a program that's long running and you use memory, you're going to need a story for memory management. So every language out there, almost every language has some story for this. I like to sort of categorize a lot of the common memory management, styles in this triangle of trade-offs. Right? So the classic one is just manual memory management, like C. This is very permissive. You can write doubly linked lists, which is great. I love them. And you can get like good worst case performance if you do it right. But of course, there's the like never-ending safety problem. So this does not spark joy. Next, there's Rust, right? Or the like static typing strategy. This has safety, modulo all the bugs in the Rust type system. And it gives you, just like C, sort of good worst case performance because it's happening statically. But of course, you can't write your doubly linked lists. And in general, the whole mantra of the type system is to restrict the programmer, right? And that also does not spark joy. Finally, we get to garbage collection, which you might think of as like the Java approach to things. And this is having permissiveness. You can write doubly linked lists. Apparently that's my goal in life here. And you have safety, but you miss out on the worst case performance. And there's going to be some garbage collection people out in the audience that are going to tell me that, but in the average case, it's actually better performance than C or whatever. That's all true. But I have actually run into the worst case performance, thrashing issues in garbage collectors in practice. So it would be really, it's not perfect in my mind. There's still a trade-off here. Okay, so the key question in this paper is we're going to say, can we reach perfection? Could someone someday invent a garbage collection algorithm that really achieves all perfect permissiveness, safety, and performance, even in really pathological scenarios, like where the heap has cycles in it and you're operating close to the memory limit? That's the kind of like philosophical question I want to get an answer to. And I did get an answer. There's some caveats that we'll go through, so take everything with a grain of salt. But the answer is basically no. This is not a surprising answer, which again, we'll get to the caveats. But it's a no even if some crazy new graph algorithm is discovered, right? Like even some kind of, like there's the Euler cycles, there's like the vertice degree 2 and everything. Even if there's some crazy new graph theory stuff that's discovered, the answer is still no. We're not going to be able to achieve this perfection. It's still no, even if the garbage collector gets to use some unlimited amount of side metadata memory. It's a fairly strong no. And this no is proved in the paper with mathematical certainty and precision. It's not just like I sat down and thought about what does mark and sweep does. It's really like a mathematical proof about all algorithms for a certain class of algorithms, as we'll talk about. So let me tell you what these sorts of difficult cases look like for current garbage collectors, right? Like you can think of mark and sweep or concurrent mark and sweep and so forth. Like what are the sorts of issues that I run into sometimes and get annoyed at? And it's kind of called thrashing. So imagine you start up your program, you allocate a bunch of regions. Okay? You call alloc 1 billion times and you fill up your whole memory. Your memory is filled to the brim. Okay? Then you make a bunch of pointers among these regions. Okay, I don't know how you make pointers. You just make a bunch of cycles and everything in there. There's some bunch of pointer relations here. Then you manipulate the pointers so that one of these regions becomes unreachable. You no longer need that region anymore. So in theory, it could be collected and reused by the garbage collector. And then you ask for a new piece of memory. Okay, you ask for a new allocation. And at this point, the garbage collector or the program runtime system has basically two options. First option is that it can actually go through and prove that that region is unreachable, prove that there is space you can reuse for the new allocation, and collect it and then reuse it and give it back to you when you call alloc, or it can just say, I'm out of memory, right? And so the second one is not desirable. It does not spark joy, again. So we always want to be in the first one as much as possible. And sort of the proof in this paper is showing that no garbage collector in our formal model of garbage collection can sort of consistently achieve this number one option here of like actually realizing quickly that something has become unreachable without introducing like unreasonably long pause times. And this is really crucially dependent on like what pointer manipulations you make here, right? Like if your pointer manipulations never insert cycles, you can do rough counting and it's fine, right? But the proof here is basically that there are some pointer manipulations that no matter what crazy graph algorithm you have, it's not going to be able to determine quickly enough that that region was unreachable. So this is just a little bit more about that. Yeah, so clear that like classic tracing algorithms suffer from this. If you ask garbage collection researchers, they're going to tell you, yes, this is what we expect. We don't expect that somebody's going to come up with some crazy new algorithm. But in graph algorithms, there are surprising algorithms. When I first learned about that Euler cycle thing, it surprised me, right? And so am I going to be surprised in 10 years that one of you comes up with some incredible new, worst case performance garbage collection algorithm? That's kind of the question here, right? So how do we kind of rule that out with mathematical certainty, even for algorithms not yet invented, even for graph theory facts not yet discovered, that all of those algorithms will fall victim to some pathological example like this? That's really the motivation for this talk. And if you're like me and you've taken some intro undergrad required computability or complexity theory course, you know the easiest way to do this is just to reduce to somebody else's hard work. Okay, and that is basically exactly what I did here. So I showed that if you have an unbelievably good garbage collector, that would mean that you could take that unbelievably good garbage collector and use it as like a subroutine to make an unbelievably good dynamic connectivity data structure. And this should actually say reachability, but whatever. Okay, so it's going to be a straight up reduction. I'm going to show you a straight up reduction in the next few slides. But first, let's pause and talk about some caveats here. These proofs are specifically about the worst case, not the average case. In order to prove things, I can't just talk about garbage collection, because garbage collection is kind of an informal concept. Do I mean, copying collectors? Do I mean in-place? So forth, right? So on the next slide and in the paper, I'm going to give you a more rigorous definition of what we mean, right? And the proofs are only going to apply to algorithms that can implement this garbage collection data structure interface that I have in the paper and that I'm going to write down on the next slide. So if your algorithm is not general enough to implement this interface, then our results don't apply to it, and you've successfully evaded this. Of course, heuristics can improve the average case. We're talking about the worst case. And language restrictions like type system restrictions can sidestep even in the worst case. But then in that setting, your collector just doesn't need to be general enough to implement the GCDS interface. I'm also going to be loose with the notion of running time here. See the paper if you really want. There's like a 20-page appendix. It's all written out there. Okay. So for the purpose of this project, what I mean by garbage collector is formalized in this kind of interface here. Okay, so you can, I won't go through this too much, but you can allocate regions, you can insert edges or pointers, delete edges or pointers in the heap. We kind of try to model concurrent collection by saying you can give the garbage collector, tell it just do one time step worth of work. And the main goal of the garbage collector is to put things on this free list once they've become unreachable. Okay, so you can see the paper for more details about this, but just keep in mind there's a formal model behind all of this of what precisely we mean by garbage collector in this setting. That is really everything and the only thing that our results apply to. So what do we reduce from, I think is the direction here. We reduce from this dynamic connectivity data structure. Actually, today I realized I've been doing this wrong. I should say reachability. The graph theory people are opinionated about connectivity being for undirected and reachability for being for directed, but I don't care that much. So basically, this is a much simpler data structure. So here you imagine you're storing a graph. The user of the data structure can add edges, they can remove edges, and they can ask, is there a path from this node to this node? Okay? That's the data structure. The graph theory people care about this data structure, or the graph algorithms people care about this data structure, and they care about proving that this is a hard thing to implement super quickly. Okay? You may notice it's very similar to the garbage collection data structure interface, and that's basically what we're taking advantage of. So I'll go through, hopefully quickly, how this reduction works, just to give you a sense. We're going to mirror the sort of graph thing that the dynamic connectivity interface cares about inside the garbage collector's view of the heap. Okay? So if the user of the dynamic connectivity data structure says to add an edge, we're going to add the corresponding edge in the garbage collection world in the heap. And if they say delete an edge, we're going to delete the corresponding edge in the heap world. And everything else is, so that's all basically the same. One thing to notice is that in the garbage collection world, we've introduced this special sort of pseudo root node X that connects to everyone else, and it's connected to by the root, meaning the stack and globals and locals and so forth. And so now the question is, what happens when the user asks in the connectivity world whether there's a path between D and C? And so you may have to just kind of take my word for it, but what you should do is this. You should sort of send some water flowing from the root to the source, D, and then disconnect X. Okay, so X was all of these guys' lifeline to root, but now the lifeline goes through D. If it can reach the destination C, then you're going to add a back edge from C back to X. And so if there was a path from D to C, then nothing becomes unreachable here. And so the nothing becoming unreachable in the garbage collection world means nothing gets added to the free list. And so that nothing being added to the free list will tell you that actually those were connected. You can walk through and convince yourself that the sort of converse works out the way that it should. And again, I'm being loosey-goosey here with some things. See the paper for details. Okay, so what have we shown? If you had a really great garbage collector in this sense, then you could make a really great dynamic connectivity algorithm. And in particular, the speed at which the garbage collector realizes that something is unreachable corresponds to the speed at which you can answer the dynamic connectivity query. But these super smart guys, Larson and Yu, showed that actually it's not possible to have a super fast dynamic connectivity algorithm. Right now, they're only at super logarithmic, was a huge deal in 2023 when they got to log 3/2. But this is it is conjectured that it's up to n or n squared or whatever mark and sweep would be. So this is a super active area of research in their community. And these results actually basically connect these two things. So we have reductions in both directions, so they're essentially the equivalent problems. Okay, so it's cool to have that kind of bridge here. Thanks. Yeah, so just quick additional results. There's always been this question about can you add cycle collection to reference counting? And so there have been attempts, and basically we prove here that the answer is no. Actually, you sort of can't without also slowing down the program for some pathological acyclic program, which is sort of surprising. So it's hard to determine when you should switch from ref counting to garbage collection, and provably hard. But we do have an algorithm that does this in the sort of optimal sense, for some sense of optimal. See the paper or ask me afterwards for that. So here's a summary of the stuff. I just wanted to say a quick thank you to the anonymous reviewers. I was sort of a maybe a belligerent author in some of the review and feedback portions, but I think the paper really was improved greatly with their feedback. So thank you so much if you're in the audience. But I'll take questions now for however much time we have left.
Right, thank you.
So the problem you're reducing to, you said it's big omega is log 3/2. What's the big O on that currently?
Oh, of the actual algorithm. I believe so these things become difficult about whether you're counting like nodes or edges, but it's like O of n or O of n squared. I think the best algorithm they have is actually the equivalent of mark and sweep.
Okay,
I don't think they have any smart algorithms.
Is the current speculation that it will not stay logarithmic? Because if it's logarithmic, on modern computers, logarithm is actually constant. It's 32 or
No. The
64
speculation is that somebody someday will prove a lower bound that's like omega n or omega n squared. Yes, and there's a conjecture called the online matrix vector multiplication conjecture that actually implies this is true. So and implies a lot of related problems are also hard. So it's kind of their equivalent of SAT being hard. So the conjecture is really that mark and sweep is the best you can do in this sense. And they believe that too, and they're trying to prove it. Yeah. Okay. Cool, thanks.
All right, thank you again. All right.
We won?
Okay, while they're fixing this technical issue, so the last talk in this session is going to be on safe tree, expressive tree policies for microservices, and the talk is given by Karuna.
Yes. Please. Thank you for the introduction. So I'll talk about a policy language and an enforcement mechanism for microservice-related safety properties. To understand the microservice design paradigm, let's consider the example of a hospital management application where a user can request for some medical test from an external lab. And in this case, the application is going to be comprised of loosely coupled components, which we call as services. So in this case, we have front end, de-identify, and lab. These services can implement their functionality by using the other services API endpoints. Like here, the front end is calling de-identify followed by the lab endpoint. Now, when a request arrives at, say, front end, or for that matter, just any other service in this application, its execution will involve a tree of API endpoints. And I refer to this execution trace of just a single request as the service tree. Structurally, it's simple. The nodes are going to be your API endpoints, and the edges will be your will denote that your parent is sending an HTTP message to the child. So in the context of our previous example, we will have front end first sending a request to de-identify, and then de-identify will have its own tree. Upon receiving a response from the first branch, will the control go into the second branch, and so on. Now, this tree actually depends upon a lot of factors and can vary across the runs. Also, the implementation of services is handled by independent teams with little to no coordination between each other. This makes it difficult and as well as at the same time important to reason about the global behavior of your application. And that brings me to the goal of this work. How do you specify and enforce the correct behavior of a microservice application? While requiring that your application treats services as black boxes, meaning we don't have access to their code, and the enforcement mechanism is non-invasive, meaning you're not required or supposed to be updating the service code to bake this enforcement mechanism into your application. Now, one might ask why these requirements? Well, it is motivated by the fact that this will help us decouple the enforcement mechanism or the policy and the application implementation. Again, why is it useful? Because in reality, these microservice applications have different teams and they have different kind of policy requirements. For instance, you might have your data compliance team wanting to enforce some GDPR or HIPAA-like compliance requirements versus your development team wanting to have some implementation-specific policies. And likewise, your testing team might want to have some conditions on which versions to use along which paths. Now, what makes it challenging? Well, as we noticed, the execution trace in microservices will be trees, which means your properties will also be conditions on this tree structure. And the existing mechanisms are unable to work with tree structures, and all they can specify and enforce are these very coarse-grained and simple policies, which I refer to as pairwise policies. To understand what it might look like, well, consider this front-end application could have written to a database or could not have been allowed to. But you will not be able to express interesting properties which actually depend upon the intermediate interaction between your front end and the database. Like, you want your database to be disallowed only if in the intermediate services you've touched upon a data belonging to the European region. Now, what was it that helped us actually come with a workaround for this challenge? Well, it is this key insight that your service trees can be viewed as nested words. This idea of nested words has been around for roughly 2 decades now. The idea is simple. You have your tree, you can consider the traversal, the pre-order traversal of this tree as just capturing the linear structure of your tree, and we'll do so as a sequence of call and return symbols. Something like you're traversing it and lining up all these API calls. The next part is to represent the hierarchical nature of your tree, meaning captures some notion of parent-child relationship. So we're able to do that if we connect or come up with a relation between your call symbols, a call to the front end, and its corresponding return. Notice that everything nested between these two symbols will be either the children or the descendants of your front end. Now, with this key insight as our center, we first design a policy language which can talk about what are your allowed set of trees, and then an automata-based distributed runtime monitor. And particularly, we use visibly pushdown automata. So in the rest of the talk, we'll first look at the policy language. I'll follow that up with the enforcement mechanism, and finally, the non-invasive implementation. Well, let's consider an example de-identification policy where your compliance team wants that you don't want to leak your personal health information to a third party. So what you want here is that front end should call de-identify only, should first call de-identify in one of its child, and then follow it up with other child, which can be lab. In SafeTree, you will have express this policy as follows. The idea is simple. You'll first start by describing what the root of your tree should be, where you should start matching the property you care for. And here I'm just saying that a tree with just any endpoint should be matched for the policy on the right. Now, what's the policy talking about? It is first specifying that the root of your tree should be front end. And then we talk about the interesting bit trying to describe that the first subtree, that there should exist at least 2 children. One of them should be a subtree satisfying the property P1, which says that it should have the root as de-identify. This will be followed by checking for the existence of another subtree rooted at lab. Now, our paper talks about other expressive language constructs to talk about more hierarchical policies like conditions over all your subtrees or conditions over all your paths. And also we support a way to just specify a regular expression and match your pre-order traversal or the linear structure of your execution. So now that we've looked at an example policy, how do we enforce that policy? The key point over here again stems from our insight that if you have a policy, you will view that as a set of acceptable service trees, which we'll mathematically model as a set of nested words. Now, the nested word literature has shown that there's this special kind of push-down automata called visibly push-down automata, which can accept certain set of well-matched nested words. And so what we do here is we have a policy, we compile it into a visibly push-down automata. And now one might wonder, do you have any formal guarantees that you offer for this compilation procedure? And we indeed prove the soundness theorem, which says that the nested word interpretation for our policy language, which we have defined, is equivalent to the language of the compiled VPA. What this means is, if you take a word that your policy says should be accepted, and if you run the VPA on that word, the VPA should go to an accepting state. And similarly, if you go in the reverse direction, you start with the VPA, run it, it's accepted, then the policy should also be saying that it is an acceptable word. Now that we've realized that our recognizing mechanism is going to be this compiled VPA, how do we implement a monitor which will non-invasively keep on looking for any violations? Well, the monitoring setup is your service, all your services running in independent containers. And the VPA that we just compiled can be approximated to just be a transition system. You start with a given state or a configuration, here represented as S, and then you see an API endpoint, which is our symbol, and transition to another state T. Operationally, this VPA is going to read HTTP messages flowing around in your application, and the HTTP message will have identifiers in its header fields, which will carry the configuration header, configuration of your VPA. And also, you can check the header and know what symbol you are reading. And then the VPA will update the state. Now, we go for a distributed design of this monitor. Why? Because a centralized scenario where you just had one VPA serving all the requests floating around in your application is not scalable. The idea is simple. You're trying to move the transitions closer to the services. What that looks like is your service containers are now going to be having co-located local monitors. Essentially, it's just the deconstructed version of your VPA. Let's say you're looking at the pink service. Lab is going to only have local monitor, which represents or encapsulates transitions on that symbol. And then the VPA configurations we were carrying in our header acts as the medium through which we coordinate between these local monitors. And we non-invasively implement using service meshes, which is a new networking layer. All that does is you have independent containers running these monitors outside your application. Finally, just to highlight some of the results, I will point out that our latency overhead and the memory overhead is quite minimal. The way we evaluate them is by taking benchmark microservice applications, running them on 9 case studies across varying number of nesting. And we noticed that when you measure the latency overhead of running this monitor, in the worst case, you've encountered only 2 milliseconds of latency, and this corresponds to a very complicated policy which has 3 levels of nesting and thousands of transitions. And another dimension was our memory overhead. You just need to carry 6 bits of configuration header, and that corresponds to, again, a very big VPA with thousands of states. With that, I summarized this work, the policy language, and the non-invasive mechanism that we've been able to implement because of this insight of treating service trees as nested words. And if you're interested to understand more about the compilation sketch or our future work talking about data dependencies and extending this work to async setting, do check out the paper. Yeah. Thank you.
Thank you. We still have time for questions.
Sure, I'll ask one. Hi, Karuna. Can you say something about how you came across the nested word formalism?
Oh, yeah.
Because I had not heard of it before, and it's interesting that it turned out to be such a good match for the problem that you were trying to solve.
Yeah. That's a good question. I have a really good answer. I think there was someone who pointed out the using regular tree languages. I don't know, someone in the audience. Yeah, we ended up looking at that because it was obvious. However, it was soon that we realized when you had to work, so regular tree languages are accepted using tree automata. They're just like your AST parsing. When we had to extend it for our setting, the way our serialized traces work, we found that extending it just made us arrive at nested word or visibly pushed down automata. And another slightly different but a technical reason is that tree automata will take in your entire tree and then process whether it is accepted or not. But in our case, in the runtime monitoring setting, you have an incrementally building trace, which means you need an automata which supports serializability, and this one was supporting it. So yeah.
Okay, let's thank Karuna again. So that ends the session, and you're dismissed for cake. If you still have space for cake, that is.
the microphone, the hand microphone has some problem. Maybe your first.
Okay, let's get started. So welcome to the last, but not the least, session of this conference, I think. And our first speaker is Xu Sheng from Wisconsin. And polynomial bounds of CFLO BDDs against BDDs.
Okay. Good afternoon, everybody. Welcome to this talk. Today, I'll be presenting our work, polynomial bounds of CFLO BDDs against BDDs, which just got accepted to TOPSLA. This is joint work with Professor Tom Raps. And now the good news is the title is a takeaway. It's 95% of what you can get from my talk. And the next 15 minutes will be about the remaining 5%, which is the proof. Now let's start. First, let's go over some background and terminologies. Let's start with BDDs. Binary decision diagrams, or BDDs, are directed acyclic graphs, representation of Boolean functions. As probably you are familiar with this, I won't go into detail, but just clarify one convention is that we will compare against BDDs without ply skipping, which means even if a node has its true and false transition pointing to the same node, we don't remove it, like the two nodes in red box on the side. Next, let's move on to CFLO BDDs. Context-free language ordered binary decision diagrams, or CFLO BDDs, are alternative to BDDs, but with a certain form of procedure calls. CFLO BDDs consist of groupings from different levels that form a hierarchical structure. The level 0 CFLO BDDs are just like BDDs for one Boolean variable. We interpret one Boolean variable and branch according to whether that variable is 0 or 1. And the CFLO BDD for higher levels, the groupings are, we don't interpret Boolean variables in itself, but instead we perform two procedure calls to groupings at level L-1. And level L CFLO BDD contains one outermost grouping at level L, which is called the outermost grouping, serve as the entry of diagram, and have some other groupings at level 0 through level L-1 that support this hierarchical structure. And we can argue by induction that a level L CFLO BDD interprets 2 to the L variables, and thus it represents a Boolean function for 2 to the L Boolean variables. Let's look at an example. F x0, x1 equals, if x0 and not x1, then 7 else 5. The CFLO BDD is on the right of the slide. Let's see how we can get f10 equals 7. We start from v0, we take the green call edge to v1, and we interpret x0 and get to v3. We have two return edges from v3, but we have to take the one that matches the edge that we entered g0, which is the green edge back to v5. And then we continue, we get to g0 again and interpret x1. But this time, we need to take different return edge, which is the violet edge from v2 to v9 to match the call edge we just entered, g0. And at last, we can get the value 7. Now, since BDDs and CFLO BDDs are both capable of representation for Boolean functions, it's natural to ask how their size compare. For clarity reasons, I will highlight the BDD content blue and the CFLO BDD content green. in the original CFLO-BDD paper, they point out that there are some Boolean functions. CFLO-BDDs are exponentially smaller than any BDD. As you can see from the previous slide, the groupings can share their colleague, like V0 and V5 share both cause G0. So in the best case, when sharing is maximized, we know that each level can contain only constant amount of structures. Each time we double the number of Boolean variables, the size of BDD will double as well, but the size of CFLO-BDD would only increase by a constant amount. So in these cases, CFLO-BDDs are exponentially smaller than BDDs. But they didn't point out the worst case. What is the worst case? Can there be a family of functions? For example, CFLO-BDDs are conversely exponentially larger than BDDs. Now let's consider one of the simplest case, which is we consider the same Boolean function and same variable ordering. There's one issue that we can spot, we can imagine and notice in CFLO-BDD is called the three-quarter depth duplication. When we interpret three-quarter of all the Boolean variables, we get to the middle vertices of the second collie of the outermost grouping. See the right picture in the blue box. And if these collies cannot share with each other, there are some kind of duplication, which means for each node in BDD, we have many different representations of that node in CFLO-BDDs. And what's worse is that this description is not specific to the outermost level. This duplication can happen at every level. Will this duplication ever cascade or propagate, like shown on the slides? If this cascade, probably it will blow the size of CFLO-BDD up exponential. Well, as you can anticipate, the answer to that question is a no. We will look at this question from another view. We pick a grouping, a CFLO-BDD grouping at level L, and assume some partial assignment alpha will lead the path to the entry of this grouping. And we interpret the same alpha in BDD B, it gets to a node N. At this point, N and G should be related in some ways. Let me explain about this. If we think of applying a Boolean function to a partial assignment, if we think in the way of like currying, we can obtain a residual function. The path, the left one which ends at N and the right one which ends at the entry of G, should both correspond in some ways to this residual function. So they are related in some ways. And if we talk more precisely, let's consider where will we interpret the next 2 to the L Boolean variables. In CFLO-BDC, it's clear that we will interpret the next 2 to the L variables in grouping G and all the collies of G. And in BDD-B, we will interpret these variables in a structure what we call BDD patch. BDD patch means the structures where we can reach, the structures that include N and all the nodes we can reach within 2 to the L steps downward. So at this point, we find out that the grouping G should simulate some BDD patch. We can have the intuition that there shouldn't be that many groupings at level L, because the number of such BDD patches are no more than the number of all the nodes in BDD. So there should be at most that number of groupings at level L. Actually, this is how we formalize the proof in the paper. We don't have time to cover that, but if you are interested, you can refer to that. And let's see, this picture is a cascading of duplication, and see what's wrong here. It's wrong at the third outermost level here. We cannot get these groupings to branch up independently like this, but rather these groupings must share. For example, the three blue collies, the three blue connections, they must share the same collie, because if we think of the BDD patch I talked about just now, we can figure out that they simulate the same BDD patch. So we can conclude about three-quarter depth duplication is that indeed it can happen at every level, but it happens independently at every level. So and the sharing prevents it from propagation. And if we look at this view, we find that we are looking directly into different levels. We do not say branch from the outermost grouping. We just look directly into level L and find that there are at most this number of groupings that can arise in level L. So we call it level locality. Now, actually, we can predict that it's a polynomial bounds from the intuition just now. But if we do finer counting, we can get a more precise bound. Let's assume that B and C are BDD and CFL BDD for the same function with same variable ordering. Then the number of groupings in C is a big O of B log B, and the number of vertices in C is a big O of B squared, and the number of edges in C is big O of B cubed. And we have also presented a tight instance in our paper, which means this is the best bound we can get. We can never get a better bound. So, as a conclusion, this paper figured out that for any function f, the BDD and CFL BDD with same variable ordering, we can say that the size of CFL BDD is big O B cubed, and we figure out this bound is tight with a tight instance. And there are some open problems that are more difficult. Like in this setting, we fix the variable ordering. We let B and C to use the same variable ordering. But what if we allow CFL BDDs to use some other variable ordering, like better variable ordering? Can we get a better bound? Like, can CFL BDD be squared or linear compared with BDDs? I can imagine this would be difficult problems. And that's all for my talk. Thank you. Thank you for listening. Do you have any questions?
Okay, any questions?
So I have a question about this concept of variable ordering. So I'm just wondering, is it the case that the best variable ordering for BDDs is also the best variable ordering for CFLO BDDs? Or are there cases where the best variable orderings for each format are different?
That's a good question. I think I can predict the answer should be not necessarily, because the key of BDD to become concise is not ordering to, say, reduce the amount of information we need to remember, but it's also about how we arrange these Boolean variables to get more sharing or reuse of substructures.
Thanks.
So the examples are sort of you using the correlations, that's Dyke, right? So, but your results is in general, like all CFL, like all the entire CFL grammar, right?
What do you mean by the? Sorry, what do you mean by the entire CFL grammar?
Like usually we work with a subset of the CFL grammar, right? We work with Dyke, CFL.
Yes.
But the result is generalizable, right?
I guess what you mean is, can we apply it to other CFLs? This is we have to we have to, I think we have to restrict the CFL or the decomposition to be acyclic, because otherwise there's recursive structure. It's more like recursive definition. It will be more expressive and complicated. And this is actually, as I said, it's two procedure calls for each, two procedure calls that is kind of equal, which means we are trying to divide the bits by half always. We can also do some other ways, like divide the bits into 3 parts, and for all these generalizations, the bound works, but it's not in the paper or in the talk.
Okay, great. Thank you.
Thank you so much.
All right. All right, our second talk is, yeah, I can see your name from. Our second talk is from Yaozhu Sun,
yeah,
and used to be a student in Hong Kong U, now in Tokyo, right?
Yeah, right.
So type-safe compilation of dynamic inheritance via merging.
Yeah. Thank you for your introduction. Oh, sorry, I forgot that. Must be here, right? And this one. Oh, does it look better? Okay. Yeah. Oh, yeah. I'm Yao Zhu from the National Institute of Informatics, Japan, and this is a joint work with Xuejing and Bruno when I was a PhD student at the University of Hong Kong. And the topic is about type-safe compilation of dynamic inheritance via merging. The first question here is, what is dynamic inheritance? Here we have an example in JavaScript. There is a pattern called mixing pattern in JavaScript that suppose you have a function mixing and it accepts a class as the parameter. Note that this is not an instance, but a class itself. And here, you return a class extends base, and base here is not a concrete class name, but a class variable. We add a new m method that returns 48, for example, here. And this pattern can be very useful if you want to add some features into an existing class. For example, you may have comparable mixing, sortable mixing, and so on. For example, sortable mixing, you may want to mix in a sort function into that base class. A problem here is how to type the dynamic inheritance. Since JavaScript is a dynamically typed language, and hopefully there is a typed version called TypeScript. And the first thing here is that we can declare a type called constructor. This type basically represents an empty class, and literally it means that it has a new, like a constructor accepting any parameters and return an empty object type. And we can type the mixing function with a generic one that we declare a type parameter t-base that extends that empty class type. And you can regard t-base as the interface, and base is a class that satisfies that interface t-base. Here, one thing we want to note is that if m exists in base, then that one in base will be overridden by the new one in the mixing. And it should be very natural because almost every existing language follows this pattern of overloading. But this overloading is unsafe. Here is an example showing that why the overriding is unsafe. And we have a new class A. A already have two methods, m and n. The m method returns a string, like here, full bar. And the n method will return the uppercase of that string. So you may notice that there is a dependency like the arrow implies. And then we use the mixing function and with A as the base class as a type parameter, as the parameter, sorry. And since here, the new M in mixing function will override the one in class A, then the dependency becomes the method N in A, and it depends on the new method in mixing. It will cause a runtime error because here M is expected to return a string, but the overridden one returns a number instead. That's why this code is type unsafe. Yeah. And a takeaway from this example is that implicit overriding is very dangerous. This example is for type safety, but if we recall the fragile base class problem, it can also cause some problem in the semantics. We will also explain this in the next example. And here we advocate a trait model with merging, which has two features. One is it will keep both behavior if there is no conflict, and it will require explicit resolution if there are conflicts, like what we have in last example. To be concrete, we will rewrite the example in our language called CP. Here, mixing has a different representation. I mean, we type it differently. Here, you can ignore the star m int part here because it does not mean too much thing here in this example. And the thing interesting is that we also have base as a variable. Here is not a plus but a trait because we have mentioned before that we have a trait model. And the class A is represented as this MKA. The M method is still a string full bar, and N is still a it still calls a function to uppercase with this dot M as the argument. But the result is different because the two M fields coexist because we suppose they have disjoint types. That means string and int does not overlap with each other. We can safely have them both in the new in the result O. This is the example for non-conflicting cases. But if you have conflicting cases, for example, here you have a mixing that adds a new method M with type string instead of the integer before. Then you can see the new M actually conflicts with the old M. And we want to avoid this implicit overriding semantics. So actually, we want to express the absence by disjointness that we suppose the base class do not have such conflicting method M with type string. And our type checker will detect such conflict and emit a warning that the two M methods actually have non-disjointness type, and they are rejected by our type checker. This is a way we keep our language CP type safe. And you may ask further, why merging matters so much in our language? And actually, it enables another feature called family polymorphism, and that can solve the expression problem very easily in CP. Basically, we will not dive into the expression problem here because time is limited. But the impression is that you have two dimensions. The x-axis here is for operation. You want to extend the operation modularly. And you also want to extend the expression modularly, like you have the numeric literals and addition. And for operations, we currently have evaluation and printing, pretty printing. In CP, it's very elegant because if we have the 4 traits before, then we can directly merge them to have a, to have a merged trait having all the 4 features in 2 dimensions. And our work focused on the compilation for merges. It's type safe, but how to make it more efficient is also a good question. The previous work will use a nested pair, like a binary tree. And the problem is, if you want to get the eval add part, the lookup is very slow because you need to go deep into the tree to find the leaf nodes. But our representation wants to solve this using a extensible record. Here, our solution is inspired by the name mangling, for example, in C++. For example, if you have many overloaded functions, you will mangle the name into different strings to distinguish them. And here, we call such mangled string type indices with the blue font here. And here, every type is mangled into a string as a record label. This is possible because our type checker ensures the expression to be merged has disjoint types. And then their type indices must not conflict here. Another advantage of our approach is about order sensitivity. Here, if we swap the merges like this, actually we need to adjust the binary tree, or you call nested pairs, to reflect the differences. So basically, we have different pairs for the two essentially same merges, but with a different order. But the compiled records are actually equivalent, and we can benefit from this actually with optimization we will explain very soon. The key ideas is to compile the merges to extensible records with type indices as labels. And in this way, we can compile dynamic merge operator to runtime record concatenation. And since our language involves a lot of type coercion, or called type conversion, as you want, typecasts, or any other words, and this feature is compiled into record filtering or reconstruction because our subtyping is more complicated with distributivity over the intersection types. And the second benefit we mentioned before can enable optimization that coercions between equivalent types can be avoided. For example, top-like types are all equivalent. Top-like type are actually the supertype of top, both supertype and subtype of top. And the intersection types are all equivalent up to permutation, duplication, and top-like type removal. This is because the records are unordered and the labels are unique. We also did benchmarking, and we find all optimizations in our work in practice. Well, the most important one is the one we mentioned, the coercion elimination for equivalent types. And CP is slightly slower than handwritten JavaScript. That's not surprising, but we are not so slow. That the most slow up here is 3 times. And most one are around 1.1 or 2 times lower. The exciting thing here is CP has the most smooth curve with regard to the inheritance level in the region example. And it means that our inheritance model is very efficient. And we have more in the paper. For example, complete examples for the type safety issue in TypeScript, compilation scheme for parametric polymorphism. And we have formalized the compilation scheme with the rock prover. We have implemented prototype CP compiler targeting JavaScript. And you can find detailed discussion on the implementation and find more optimizations here. You can scan the QR code to find our benchmarking suite, prototype implementation, and the formalization in Rock. Thank you very much for your attention. Please feel free to ask me any questions.
Thank you. Maybe we'll have time for one question. Somebody, yeah.
Thanks for the talk. So when you compared to JavaScript, what is it exactly that you compared? Was it dynamic inheritance in JavaScript or something else?
Yeah, for maybe I haven't mentioned, the dynamic inheritance is compiled to merges. And actually, if you write class in extend something, actually we have like class A merged with class B. A is the current class you have in the body, and B is the inherited class.
So your benchmarks, they show that this approach is faster than doing it the JavaScript way, right? Or is that?
Right, yeah, our benchmarking implies that result. But we want to mention that the handwritten JavaScript one is also in the similar style with us. If maybe you can look into the example to have more deep understanding on that. But actually, it may be not so idiomatic in JavaScript.
Okay.
Yeah.
Sure.
Yeah.
Thanks.
Yeah. By the way, it's also for the sake that it must satisfy the expression problem.
Okay, maybe carry the discussion offline. Okay. Thank you.
Yeah. Thank you very much.
All right, the next 4 talks are remote, and our next speaker is Marco. The title is Detecting and Explaining Inequivalence of Context-Free Grammars. So Marco, can you hear us?
Yes, I can.
Yes, please, go ahead.
Thank you for the introduction. Hi, I'm Marco, and I'm a PhD student at Ruhr University in Bochum, Germany. And yeah, there, my team and I develop a tutoring system for students. And now our paper is about detecting and explaining inequivalence of context-free grammars. All right, let's jump right into it. A typical exercise you would pose in theory courses, bachelor theory courses, you probably have seen them in your own courses as well, is, let's just have this figured out. Sorry about that. Yeah, there we go. All right. We have this task which asks students to provide a context-free grammar for the language that is given right there. And, well, the question is, what should the system answer now? We would like the system to give feedback on this task. And what we ideally would like to have is that the system can determine the correctness, like is the grammar correct, and also to give some feedback and explanation on mistakes, like pinpoint the mistakes. For example, we would expect feedback. Well, your language describes, or the grammar you provided describes the word AAB, but that's not in the language you should describe. Or even on a high level, which is more interesting, that we can provide the language that the student have modeled by their grammar, or even tell them, oh, well, look at this specific rule, this might help you to solve your problem. So that's our main goal, give high-level feedback that really tells the student something about their mistake. Well, and that is difficult, because, well, even deciding the equivalence of context-free grammars is undecidable, so providing this feedback is even more challenging. So what can we do? Our framework offers a solution to that. We combine several factors to provide this kind of feedback. Of course, not in all cases, we would solve an undecidable problem, but in many cases. So we use grammar transformations, we use a subclass of context-free languages and algorithms from that subclass, and also a grammar canonization method. And this talk, I'm going to first give you a glimpse into our framework and tell you something about it, and then also give you a very little peek on how we evaluated it on real data. Great. So first, let's focus on the feedback of the type. You might look at this production because that might help you figure out what you did there. For this, we use transformations. And before I look into this specific feedback or this explanation, let's first look into how to determine correctness of a grammar by using transformations. Right. We use equivalence transformations on grammars. They can be as simple as we remove unnecessary non-terminals, like non-producing or non-generating, for example. But it can also be like a little bit more advanced and non-standard things, like here getting rid of one reduction level, which is not necessary. That's an example on the slides. And to be flexible, to specify these transformations and also specify them in the descriptive way, we designed a new transformation language and call them pattern-based transformations. They use the style of, we have patterns, like we basically replace non-terminals by pattern variables and offer some syntactic sugar on that to be able to specify transformations in a nice way. Now, for testing equivalence, our procedure is to design a pipeline. We designed a pipeline for normalizing grammars, like a pipeline which pipelines all these transformations together. And they don't have to be that linear, but instead, the result of such a grammar can also be multiple grammars, because the transformation can be the application can be non-deterministic. Yeah. So right. Let's go ahead. Now, if you have this pipeline and this normalization method, when a student comes in and we want to figure out whether it's equivalent, we can normalize both the student attempt with our pipeline and the solution with the pipeline again independently, and then check whether the solution sets we have, whether they match. So if there's a one match, then we know, okay, we can transform the grammars equivalently from this end and from this end. So the student's attempt has to be correct, that is equivalent to the solution. Now, if you want to generate hints, like tell them, that's what you did wrong, look at this rule, then we can use non-equivalence transformations. We call them bug-fixing transformations. Our goal, and these bug-fixing transformations describe corrections of typical student errors. So our goal is to apply such a transformation, and now if you apply it to a student submission and get a correct grammar, we know that our transformation actually fixed that error, so we kind of have an idea what the students did wrong here. And then we can return that part of the grammar that we changed as that's where the error lies. At least that's one way of describing where the error lies. There might be other ways as well. Yes, okay. That was the very short description of the normalization framework, about transformation framework. Now let's jump into another perspective, and that's providing feedback of the kind, well, you actually modeled this language, but you should model a different one. For this, we use bounded languages. A little definition what they are. Well, a language is bounded if it has a fixed structure, or if every word has a fixed structure. More formally, language is bounded if there are words such that every word of the language is a repetition of these words in a fixed order. Like every word consists of the same blocks, and only the number of repetitions of the blocks differs. For example, and these words, these blocks, is called the boundedness witness. For example, the language a to the m, ab to the m is bounded because it has the bounded witness a and ab. Great. So why is this class useful for us? Well, it's useful because it has useful properties, and I show you two of them. Given any arbitrary conditional grammar, it is decidable, and even in polynomial time decidable, whether it is bounded for any witness. And if I have a witness, I can also test it against this specific witness and tell it whether it's bounded concerning this specific witness. And even more important, or more interesting to us, the equivalence problem is decidable as soon as one of the given grammars is bounded. That was proven in like 1964 already. It was a non-constructive proof. We had to figure out how to put that into an algorithm. But yeah, that's very, very nice property, because that enables us to use this kind of algorithm as sketched here on the slide. So to provide such a feedback, first we check whether the solution, the student submission is bounded by the same witness as the solution. So whether they have the same structure, all words have the same structure. If that's not the case, well, we can tell the student directly, well, your grammar describes words that don't follow the structure. But if that's fine, then we make sure to use distinct symbols for the different blocks. For example, I go back to slides. In the example here, we have A and AB. So they are not disjunct. The A is present in both. So when we use now individual symbols for them, then we can use the paric image to describe how often the blocks appear. And that's exactly what we want. So we can represent the paric image then as an extensional Pressburg formula. And having that, we can either test for equivalence by just testing for equivalence for these Pressburger formulas, or use the formula to provide a set notation of this language the student modeled. So the structure is the left-hand side of the set notation, and the Pressburger formula is basically the right-hand side. Now I showed you two main aspects of our system, and now it's time to build that all together. I give you an overview how this all interacts in one framework. Let's start with the normalization we've seen in the beginning. With that, we can check whether a grammar can be transformed into a grammar which is where we already know the correctness or the incorrectness. And we also looked at the bug fixing transformations and saw that they can be used to generate more feedback. Yes. Let's now look at these more basic tests, like testing for counterexamples, as many systems actually do. You can easily test for emptiness, like whether the language the student modeled is empty, and then give feedback if the language is not supposed to be empty. Same for finiteness. And by just looking at the paric image, we can also give feedback on the symbol frequency. Like, for example, your language should, or your grammar should describe a language which has, where all words have twice as many A's as B's, but in your language, it's twice as many B's as A's, for example. We also looked at bounded languages. There we can test whether the solution and the student submission are bounded by the same witness, and if so, also test for equivalence. And if all that fails, if it's not a bounded language, if none of the methods for all target languages work, then we don't have a decision. Then an instructor has to do that manually. A central component of our system also is caching. That is, we also not just cache every attempt, but we make sure to cache canonizations of the grammars. That is, we make sure to, it's basically the same thing as graph canonization, where you look for a unified naming of the nodes. Here it's unified naming of the non-terminals. That makes sure we don't cache the structurally same grammar twice. Yes, that's our framework. And now just very quickly look on the evaluation on real data.
Can you wrap up in 1 minute?
I can. We evaluated our data on 3 data sets collected in 2 tutoring systems. So in total, we had 55,000 attempts. And what I will show you here is in how many cases we could discover the equivalence. And that is, for these 55,000 attempts, we only had to look at 260 single cluster, that is 260 60 attempts, that's about 4%. And in many exercises, we didn't have any attempts that our system couldn't evaluate on its own. Yes, so we developed this framework and evaluated it on real data. It is integrated in a real educational support system, ILTIS, where we use it for 2 semesters now. And yeah, thanks for your attention. I'm happy to answer any questions.
Unfortunately, we don't have any time for questions. I hope that you contact the author offline or ask questions on Discord. Let's thank the speaker. All right, thank you. Let's switch to the next one. All right.
Hello, everyone.
Yes,
my name
great.
is
You can hear us? Oh, pre-recorded. Oh, okay. All right. I didn't know that. Okay, sure. Then just play it.
This is my crew. I will be presenting our paper, Model Abstractions for Virtualizing Memory Addresses. So let's first discuss virtualized memory from systems perspective. So virtualization is a common concept that appears in multiple different systems design, but for memory virtualization, we can concretize the practice of using it as a virtual pointer pointing to a physical page. I mean, supposedly allocated physical page. And memory virtualization, as most of other virtualizations, are done for creating the perception of abundance. So memory virtualization basically creates the deception of having more memory than we actually have. And memory virtualization is realized in an well-known abstraction called address space. We can think of address space as a named container for virtual to physical memory mappings. So the core mechanism realizing the memory virtualization is called address translation, and it's implemented with data structure called page table trees, or like sparse page table entry trees. Here is in the middle we see 4 levels of tables realizing a sparse page table tree. At the top we see a virtual address including indices to each level of this tree, and here at the bottom there's a unique root address to that tree. And basically the traversal is traversal basically starts at the level 4, top level, and each time for the next level we calculate the next level's table's address and get the index for that table's entry from the virtual address, and then access to that entry. And when we are done with each level, we will be finally reaching to the physical page. Here we see a rough outline for the address space abstraction. At the top, we see designated control register CR3 pointing to the name of the address space root, which itself is a unique root address of the page table tree of this address space, which sits in between virtual addresses and physical addresses, VA and PA. And when this designated control register points to an address space, then the current view of the memory basically becomes the memory layout of that address space. So why we care about virtualized memory? We care about it because it's one of the core pieces in the kernel that provides resources to the rest of the kernel, pretty much to the complete rest of the kernel. And we think that when we understand this piece rigorously and mathematically, we will be able to understand the rest of the kernel more properly. So before getting into the mathematics of virtualized memory, we should speak about some important aspects of virtualized memory. So here we see on the right a function at the bottom, walk page directory. It's basically implementing the address translation, like traversal of the page table tree, which calculates the root address of the next table, and then get the index to the entry for that level from the address from the virtual address. And if that entry does not exist, then basically it allocates and puts it in there. So it modifies, it changes the shared physical page table tree, page tables. So this is important because, like, if this is done without following any protocol, like accessing and mutating these shared physical page tables, would cause all the other virtual to physical memory translations in the same address space to be invalid. So up until now, we were inside the address space. But now if we take a step back, we will see that there are multiple address spaces in the kernel, and these are like managed by the component called Virtual Memory Manager. And one of the most essential functionality of Virtual Memory Manager is basically switching in between address spaces. And it's basically loading the address space name or identifying piece to the designated control register CR3. So here as we see on the top, inline assembly, it's basically one move instruction loading the CR3. Now we have pointing the root I with the CR3, and then we will switch into the root J by loading root J to it. So now, now we can look at the virtualized memory from the logical perspective and understand the verification challenges that it exposes. So first, since our assertions for the virtualized memory are in separation logic, we should take a quick recap on separation logic assertions. Most importantly, the most crucial one in our context is called points to assertions, or like named ownership assertions, like memory reference points to a value, like heap value. So these we can think of them like as a token as a logical token to an underlying physical resource. So they can be either fragmental tokens or fully owned tokens, where the full ownership grants the access to change the underlying resource associated with it, and fragmental would give you the non-mutational accesses. And so on top of our machine semantics, defining the register points to and physical memory points to were straightforward. But as you might have already noticed, like virtual points to is a little bit tricky. So a naive attempt to define the virtual points to relation would be like giving a definition to it by in terms of like unfolding physical points to assertions describing the accesses to the shared page tables at each level. However, as we discussed briefly before, like this assertion would not be sound under the existence of any virtual memory action mutating the shared page table, which we already saw, which we already spoke about. So we need to find another way. So what we propose is to define the virtual points to relation in two pieces: traversal of the page table tree and access to the underlying physical page. The traversal piece is abstracted via a fragmental token summarizing the traversal of shared page table, and these tokens are distributed to all virtual points to relations in the address space. So the second piece is, as expected, like is fragmental physical points to the physical page to look up the to read the page, physical page. By having this kind of form, we basically recover the soundness of address translation, because when the protocol enforces having the full ownership of the traversal token to change the underlying shared page table tree, page tables, which resides inside a persistent invariant. So after fixing the problem on address translation, now we can focus on the address space management. So we know that virtual to physical mappings are only valid in a certain address space, but we can never infer this from these mappings because they are unaware of the address space they are in. So we reflect this fact into our assertions by lifting the relevant propositions, which we call VPROPs, with the unique identifying root address of the address space, and then we relate the address space with its virtual points to relations in a modality called address space modality. Here we see P rooted at R, asserting that all the virtual points to assertions in P are valid only under the address space identified with R. So let's pull things together. We spoke a lot. Let's pull things together in an address space switch example. So here we see two address spaces with the root addresses root I and root J, with virtual address mappings for the addresses VAI, VAJ respectively, and currently loaded memory is root I's memory, as the control register is loaded with it, is pointing to it, and as we see in the precondition, root I's virtual mapping is loose in the specification, but root J's is under the address space modality. So, but when the address space switch happens, CR3 is loaded with the root J's name, and then name root J, and then the mappings of root J address space will be loose in the specification in the post condition, and root I's virtual mappings will be put under the modality, address space modality. So it's a neat, clean specification of an address space switch, but I think it's worth highlighting some of the subtle aspects in this specification. So we have the resource context duality in here. What I mean by saying that is basically we have two address spaces mentioned in the specification, which is either the current one or the one to be loaded into the control register. So this duality allows us to have the luxury of not annotating the virtual points to assertions with the root address space names, like VAI points to PAI does not include that form of the form of this assertion does not have any naming related to root I. So this is pretty much what I would like to say. This is a gist of what is in the paper. So there's a lot in the paper. There are more other critical pieces of VMM discussed in the paper and verified, and subtle aspects of kernel invariant is also in the paper, and large soundness proof is also in the machine. We have a huge machine check soundness proof for our machine model, and also we have some discussion on our machine model in the paper. So right now this is the end. I'm on the postdoc job market. If you think that I will be a good fit into your research context, then I will be grateful if you reach to me, and now I'm happy to take questions. Thank you so much.
I guess we can ask questions on Discord and email the authors. Let's go to the next talk.
My name is Hongbo. Today, I and my collaborator, Quan, are honored to present our work, a new verification framework for confidential computing. Our work focuses on a fundamental challenge: how can we trust the software running in secure enclaves? Agora's design features trustless and open more. We'll explain how we achieve these two goals. Let me get started with a quick review of confidential computing. It relies on hardware-based trusted execution environments, or TEEs, to protect sensitive data while it's being processed. TEEs provide encryption and isolated execution, meaning that we only need to trust the hardware, not the host operating system or hypervisor. Remote attestation gives us a way to verify integrity of the code running inside the T, but this also brings us a critical question. Is code integrity enough? Simply putting code into a T doesn't automatically make it secure. Attestation confirms what code is running, but it doesn't tell anything about its behavior. We're often interested in deeper security properties like fault isolation, information flow control, or side channel resistance. Unfortunately, existing verification techniques have significant drawbacks. They often result in a large trusted computing base, or TCB. Also, they are tied to specific security policies and rely on a closed ecosystem of tools, which limits our ability to outsource verification. Let's look closer at problems with existing verifiers. A major issue is the big TCB problem. General purpose tools like Anger are powerful, but they are also massive. We're talking about tens of thousands of lines of code for the analysis engine and hundreds of thousands for the underlying SMT solver. Even well-tested tools have bugs and vulnerabilities, and if we need to verify multiple security policies, the TCB just keeps growing. The second major problem is the closed nature of the current verification ecosystem. We're forced to trust a small set of well-known tools and solvers. This makes it difficult to incorporate new, cutting-edge verifiers from the research community without blindly trust them. Our goal is to break open this closed model and create a verification framework that is both trustworthy and open.
The first innovation of Agora is to move the complex proof generator, such as static program analysis and logic-based proof system, out of the TCB. This diagram illustrates a canonical approach, which simply runs the verification workflow into TEE. Based on the policy, the program analysis generates a series of assertions for the binary to be verified. Such assertions are facts related to security properties. Such generated assertions is then sent to a trusted SMT solver, which then derives the verification result. The verifier finally signs the binary for releasing. Usually, to verify one policy, a dedicated verification framework is required. This can bloat the TCB size easily. Our first key design principle in Agora is to move the complex program analysis out of the TCB. Instead of trusting the analysis, we treat its output, that is a set of assertions, as untrusted. We then use a much smaller trusted validator to check these assertions. The core idea here is that verifying a proof is significantly easier than generating it. This allows us to leverage powerful, untrusted analyses without expanding our trust base. To illustrate this, let's look at a case study with conf-LLVM, a compiler that enforces a coarse-grained information flow control policy. Conf-LLVM uses type annotations to label sensitive data and then compiles the code to ensure that private and public data are stored in separate memory regions. They essentially state that any instruction accessing memory must use the correct segment registers, GS for private data and FS for public data. Moreover, it encodes the sensitivity of function arguments into a magic sequence to ensure correct information flows through function calls. The key takeaway here is how the security policy is encoded into the binary. For a policy like the one in conf-LLVM, the assertions are relatively straightforward. An untrusted information flow analysis performs a complex label inference and generates assertions. Then, the validator's job is to simply check that every memory access in the binary follows this rule. This validation logic is incredibly simple, requiring only a few hundred lines of code, replacing the large and complex program analysis. But what about other security policies? We don't want to build a new validator for every policy. This brings us to our second key design innovation, a generic policy-agnostic assertion language. This language allows us to express a wide range of security policies, from software fault isolation to side channel mitigations, without having to change the core validator itself. Here you can see the grammar for our assertion language. It is expressive enough to capture the low-level details of program execution, allowing us to define complex security policies in a standardized way. The language is also designed to be extensible, so we can add new predicates as needed to support future policies.
Before moving to the last key design, let me introduce blockchain and smart contracts shortly. Blockchains provide a decentralized and transparent ledger, and smart contracts allow for self-executing agreements. This model of transparent and verifiable computation is a key building block of Agora. We moved program analysis out of the TCB, but what about the SMT solver? This is often the largest and most complex part of any verification toolchain. Our third key innovation is removing the SMT stalwart from the TCP entirely. We do this by reframing the problem. Instead of trying to prove a property is true, we challenge external bug hunters to find counterexamples. If they can find a set of inputs that violates a property, they can submit it and win a bounty. The insight here is a checker is much simpler than a full-fledged SMT solver, which dramatically reduces the TCP. Of course, designing such a system has its challenges. A key issue is measuring the effort of bug hunters when no bugs are found. To solve this, we introduce a fabricated tasks with known solutions and small rewards, and mix them in with genuine tasks. This ensures hunters must actually work on problems to claim any reward. To provide a baseline level of assurance, we can also run reference solvers. Finally, the entire process is managed by blockchain-based smart contract, which provides auditable confidence in the results, even though they came from untrusted sources. We have implemented a prototype of Agora. This includes a banner verifier, assertion validator, and the smart contract for the bug bounty system. We also have developed untrusted assertion generators for 3 different security policies. The entire project is open source and available on GitHub. Now for the results. The circle part compares the TCP size of Agora to another verifier. As you can see, our trusted components, especially the banner verifier and bounty task manager, are almost 2 orders of magnitude smaller than their counterparts in a general purpose framework like Anger. This demonstrates the effectiveness of our trustless approach. More importantly, look at the policy-specific code. To verify SFI, Agora requires only 625 lines of code, whereas a dedicated verifier like VeriVas needs almost 2,000. For information flow control, it's a 335 lines for Agora versus a 1,000 plus 500 lines for ConfVerify. This demonstrates that our generic framework is not only smaller but also more efficient for adding new policies. Moreover, we can support verification of an LVI mitigation in only 77 lines. We get strong security guarantees with a dramatically smaller trusted computing base. To evaluate Agora's correctness and versatility, we implemented verifiers for 3 distinct security policies. First, for software-based fault isolation, or SFI, we successfully verified binaries from the entire SPEC 2006 benchmark. Our results matched those of specialized tools like VeriVas, proving that our general framework doesn't sacrifice capability. For information flow control, we tested Agora on real-world systems, including Nginx and OpenLDAP, and successfully verified them. More critically, we also ran negative tests. We intentionally tampered with binaries by altering magic sequences and segment registers to create data leaks. Agora correctly identified every single violation and rejected the malicious binaries. Finally, we verified the mitigation for load value injection attacks, successfully confirming that the policy was enforced correctly across the SPEC 2006 benchmark. Together, these results show that Agora is a correct, robust, and flexible verification system. Thanks a lot and hope you enjoyed the talk. Please let us know if you have any questions. To summarize, Agora is a novel verification service engineered for confidential computing environments, specifically designed to address the major problems of the large TCP. we achieved minimal TCP by offloading traditional complex components, namely static program analysis and large SMT solvers, outside of the trusted boundary. Instead, we rely on a lightweight validator and a checker for outsourced results, embodying the principle that checking a proof is easier than constructing.
Oh, and it, all right. So I believe the author is online. So if you have any question to ask, the author can hear you, I believe. Well, I guess I can ask a question since they're online. But if they're offline, then we'll go to the next one. Are they really online?
Yes, we are here.
All right, just a simple question. When you verify the result using a bug bounty, you mean human-based bug bounty, or you're using a metaphor for this?
Could you please repeat the question?
Yeah.
So you remove the Z3, right, from the TCB, and you designed a blockchain-based bug bounty system to challenge. So you mean really the human-based bug bounty system, right?
Yes, exactly.
So why not just using some kind of trusted encryption-based communication between the constraint solver and for verification of the results? I'm curious why using a human-based bug bounty verification mechanism.
Yeah, so I guess I can take this. I guess we already discussed this in the paper and in the earlier slides in the presentation. So SMT solvers or serial provers in general has flaws. They have bugs that can invalidate the results. So we do use them as reference, like bug bounty hunters, but we don't fully trust them. That's the main reason for introducing human, actually not exact human bug hunters. Really, they are just more instances of solvers. Like you can introduce hundreds or thousands of different solvers, like distributing the computation power needed to verify a binary.
It's a recorded talk, right? And the author is also online, or
my name is Jessica. I'm a PhD student at the University of Pennsylvania, and I'll be talking to today about our paper, QED in Context, an observation study of proof-assistant users. It's a good time to be a proof assistant. Over the years, proof assistants have been used to tremendous effect to verify the correctness of computer programs, with well-known results including a C compiler, cryptographic algorithms, and an operating system kernel. In the past few years, proof assistants have also enjoyed a surge of popularity in the mathematics community, especially due to the lean prover and its mathematical library MathLib. And of course, proof assistants continue to be a recurring character in your friendly neighborhood PL paper, which might include a mechanization of the paper's results. An important technology like the proof assistant needs to be usable. There's lots of folklore knowledge about proof assistant usage, but for people building these kinds of systems, we need a more robust understanding. Our paper aims to do just that. We present an overview of proof assistant usage that is shaped by the results of our qualitative user study. This overview is carefully organized. There are many overlapping, entangled processes and subprocesses involved in proof assistant usage. We provide a structured way to think about these, so that this paper can be a starting point for getting a sense of what it's like to use a proof assistant. We also share a lot of concrete data. This includes examples that users encountered with real proof snippets, counts that show how widespread a pattern was, and lots of context about what users were thinking and saying. We hope that this results in a catalog of usage scenarios that future tool builders can draw from for inspiration. I'll now share with you a bit about our study methodology. Our study had 30 participants. Half of them used ROC and the other half used Lean. We observed each participant for about 1 hour. Our median participant had a few years of experience with their proof assistant. And since we observed participants doing their own work, we saw formalization projects from a large number of domains. We chose to structure our study around observing real proof work in real time. The particular approach we used is a well-established methodology in HCI research. It's called contextual inquiry. Let's talk about what contextual inquiry looked like for our study. The sessions were Zoom calls with the participant P and the observer O, that's me. We asked the participant to do the work they normally would, while screen sharing and narrating. One important thing to know about contextual inquiry is that it calls for the observer not to observe silently, but instead to take advantage of the fact that we are there in real time and observe as an apprentice would. This includes interjecting to ask clarifying questions, such as, "Why did you do that just now?" as well as offering our own interpretations and asking the participant to confirm or correct them. Using the recordings, we transcribed each session, including both what was said and what they did, and we qualitatively coded the data by tagging snippets with themes. So what did we learn from all that? We organized our findings into 4 perspectives on proof assistant usage at different levels of resolution. Proofs in motion, conversing with approver, proof sources and resources, and beyond QED. For each perspective, we'll share just a slice of what we learned. The first perspective we call proofs in motion. We were able to observe in live motion what it looks like for proof writers to incrementally develop their proofs, often in iterative and nonlinear ways. One source of nonlinearity was context switching, when proof writers temporarily skip their current goal and work on another part of the proof instead. This might be done on the fly, for example, to jump to an easier goal or a harder one. Or the proof writer might deliberately start by sketching the skeleton of their proof, leaving holes to be filled in later. When proof writers engaged in this micro-interaction of context switching, they implicitly relied on a very powerful feature of the proof assistant, its ability to resupply the proof state on demand. One participant remarked on this explicitly, saying that context switching is much cheaper in a proof assistant than on paper. That's because on paper, contextual information is just in the back of your head, and then if you switch contexts, you forget what exactly was in the back of your head. These examples and others show how proof writers leverage proof assistant feedback to facilitate their proof efforts. Of course, using a proof assistant is not all sunshine and roses. Our second perspective focuses on difficulties proof writers encounter when trying to speak the proof assistant's language. A frequent source of difficulty is precision. Proof writers often have to spend time getting the details of their proof script precisely right. Consider this example. This proofwriter wanted to do case analysis on the length of P. But in the base case, they encountered a proof state that looked roughly like this. The information that P has length 0 is missing, so the goal is impossible to prove. After some fiddling, the proofwriter decided to pivot to a different approach. What would have fixed the problem? An H colon. Now, there are many possible diagnoses of what went wrong here. The proofwriter noted that this is not a tactic they use frequently, or maybe the issue is with the documentation, or maybe the design of the tactic itself. The thing I like about this example, though, is that it adds some color to what we mean when we colloquially say that proof assistants are difficult to use. In particular, not only do proof assistants require precision, it does so sometimes at the granularity of characters. Even though we are observing individual proofwriters, often working on individual developments, they still made frequent and substantial use of existing proof sources and resources. This included both relying on existing mechanized proofs, for example, searching for lemmas, or reusing proof snippets, as well as bridging the modalities of mechanized and paper proofs, for example, translating from natural language proofs or doing some scratch work. We see in this section that proofs build on proofs, and experienced proofwriters know how to do so effectively. Our fourth and final perspective is a bit different. Now we look beyond the process of simply getting to QED and examine what qualities proofwriters value in their proofs. But let's pause for a second, because you may wonder, if the proof assistant is checking the proof, do proofwriters actually care about anything other than compilation? They do. We saw many examples of proofwriters making subtle but intentional choices that reflect what they value in a proof. If we only looked at the before and after of the choices proofwriters make, we might not know how to interpret them doing things like adding a word that has no visible effect, or choosing between two tactics that both solve the current goal, or even flipping the sides of an equality. But because we were able to talk to proofwriters about their decision-making in real time, we were able to learn that they wanted to improve the maintainability by localizing future failures, that they wanted to communicate their mathematical intent by opting for a more specialized tactic, and that they needed to follow the conventions of the library that they were contributing to. We can't necessarily tell by just looking at a finished product, but proofwriters often invest careful thought and effort into how they write their mechanized proofs. Okay, let's zoom out again. Our paper's findings are organized into 4 perspectives. Proofs in motion, how proofwriters leverage proof assistant feedback to engage in iterative, nonlinear proving. Conversing with the prover, the sources of friction that arise when trying to speak and understand the proof assistant's language. Proof sources and resources, how proofwriters build on existing proof work. And beyond QED, that proofwriters care about how they express their proofs. Of course, what we've covered today is only a subset of what you can find in our paper. We talked about context switching, though we also observed proofwriters iteratively revising their specifications and extracting lemmas in the middle of a proof, as well as engaging in small stakes trial and error. We talked about issues of precision, though we also observed proofwriters encountering difficulties with understanding what the proof assistant was saying, such as due to the complex proof states or confusing error messages. And of course, we also go into much more detail about how people utilized existing proof work and the considerations they had beyond QED. The final thing I want to convey is that if you like looking at tools from human-centered perspectives, hello, I hope you consider looking into proof assistants. In particular, we hope that our paper might be useful to folks interested in people and proof assistants in a few ways. For those that don't know how proof assistants work, our overview can help onboard. For those with existing intuition about proof assistant usage, we can help them add complexity and nuance to their understanding. And for those building tools, our examples can help serve as inspiration for case studies. Thanks for listening, and I'm happy to take questions.
All right, thank you. And the authors are online.
Yes, I'm online.
Testing, can you hear me? Okay, so...
Hear us? Can they hear us?
Can you hear us?
I can hear you, yes, sorry.
Okay, excellent.
All right, go ahead.
Very excellent overview. And you can interpret my question more conservatively or go completely blue sky with it. Based on what you've seen, what do you think could be done to improve the usability of theorem provers?
Sorry, I'm just processing the question. You asked based on what there's an echo. Can you hear the echo? Okay. Yeah, so based on what we've seen, what we think could be done to improve the usability of proof assistants. I think sort of I'll give you sort of a more fuzzy direction and a less fuzzy direction maybe. I think a more fuzzy direction, one thing that I've long been interested in is sort of what would it look like to reimagine a proof assistant to be optimized for exploration, by which I mean things like trying to iteratively figure out what definitions you want or how you want to approach the proof. I think there's this interesting tension where, on the one hand, proof assistants are really good for iterative, nonlinear, exploratory kinds of proving because of the sort of automated, instantaneous, up-to-date feedback. But then there are also, of course, ways in which proof assistants are really bad for exploratory proving because of the sort of high burden having to deal with all these unimportant details that are especially unimportant during the exploratory phases. So I'm interested in like figuring out how can we reconcile these things. I don't know. If you figure it out, please let me know. And something less fuzzy, I think there's lots of things to be done from sort of pedagogical perspectives on making persistence easier to learn. I think one thing that really stuck with me is the participant was talking about how when you're usually learning a programming language, you can learn some building blocks or some general principles that you can then compose into being able to write more complex programs. But proof assistants, tactic-based proof assistants, have a feature where you have to learn tactics on a tactic basis because it's sort of black box things, and that has interesting sort of pedagogical effects. And there are also sort of really interesting, challenging processes like lemma extraction and lemma search, to give examples that I think are interesting to delve into further. I hope that answers your question. Feel free to follow up afterwards if it doesn't.
I think it's great someone is looking into this. It's super cool. I was wondering if you found any difference between the way, say, a mathematician approaches proofs, someone who has a lot of experience writing paper proofs, and computer scientists that maybe learned proofs by just using ROC or Lean.
Yeah, so differences between how...
Sorry, Jessica, the internet is... Can you turn off your camera? Maybe
okay,
the sound would be much better.
Can you hear me any better now?
Yeah, much better.
Okay, sorry about that. So the difference between how a mathematician who's used to paper proofs would write proofs versus a computer scientist, I think that's actually like quite related to what we're looking at currently. In the context of the QED and context study, I don't know that we've really sort of collected data exactly along those boundaries. I think, let me think if there's anything interesting I can say about that yet. Yeah, I think that wasn't sort of a dimension along which we really made comparisons. I think it's a really interesting question. I think there's various ways that you could sort of do format a study to a more targeted study of that question. There's sort of the natural sort of differences between Lean and ROC, for example, where Lean is sort of more mathematician heavy at the moment and ROC is more computer scientist heavy at the moment. And so I think there are comparisons that could be made there. And then, sort of various other study formats, some of which we're attempting, about sort of how people's different backgrounds and relationships with paper proofs affect their experience with proof assistants. Yeah, I think it's a really interesting thing to look into.
Thank you so much for the talk. This is such great work. My question is maybe a little abstract, but if someone were working on tooling for proof assistants, what is like the one thing you would like them to constantly keep in the front of their minds as they're doing it from everything that you've learned?
Okay, so if someone were working on tooling, what is one thing they should constantly keep in mind while doing it? I think it's that sort of proof assistant users tend to have a lot of knowledge about sort of how to approach their proof and how to use their proof assistant. And so even when they are struggling to sort of complete the detail in exactly the right way, that doesn't mean that they're 0% of the way there, right? They're actually probably like 80, 90% of the way there. They might know exactly what tactic they're supposed to use, what sort of proof strategy they're trying to go for mathematically. They might understand, like sort of broadly speaking, what their problem is, but not exactly how to fix it. And so I think sort of ways in which we can design tooling to leverage the sort of things that proof assistant users already know about their problem and potential solutions to it would be interesting to me. Sorry, that's maybe an answer that is abstract as the question. But I think to be a little more concrete, I think, given the recent emphasis on automatically generating proofs, I would be interested in sort of what would it look like to make maximum use of what people already know about their proof assistance and their proofs.
Very cool, thank you.
Last question.
Thank you for the work on something that the community really needs, which is the ACI aspect of theorem proofers. I was curious about the interplay with the lemma searching or proof search. So I'm talking the suggest tactic in Lean up to just using LLMs or even the Lean GPTF tactic. Did you see its use, or did people try to use those searches before doing it manually, or the other way around?
Just to make sure I processed your question, so asking about lemma search and proof search from sort of like automated tactics up to LLMs.
Exactly.
Yeah, so we definitely saw a lot of people using like what we called proof resources to engage in, for example, lemma search. Lemma search took varying levels of automation from sort of, the standard rock search tactic, for example, which is very much requires the user to construct their own query, to something like Moogle, which is Lean's sort of natural language-based search engine. So we definitely saw some of that. In terms of like language model or things like Copilot, we saw like a few instances of Copilot. I think 3 participants used it. We did sort of make a deliberate choice not to sort of focus too much on the Copilot instances, both because there weren't that many of them, and also because we think that like a more targeted study would have been better there. So the answer to your question is, like, we saw certainly a lot of lemma search and searching for things generally, a little bit of sort of more LLM usage, but not that much.
Okay, thank you so much.
All right, great. Right, so let's conclude the session. Let's thank Jessica again for the great. All right, that concludes the session and concludes today and concludes the conference. And on behalf of SPLASH'25,